Hello wonderful person, this is Anton, and in today's video we're going to focus on TRAPPIST-1, the system that was very recently in the news on Google Doodle and pretty much everywhere else. Everyone was talking about it because we've discovered that this particular system has 7 Earth-like planets orbiting around it, and so possibility for discovering life there is maybe, just maybe, somewhat high now. We're going to discover what the system looks like in Space Engine, also what NASA thinks it looks like using their own simulation known as Eyes on Exoplanets, and we're also going to speculate and do some science. Welcome to What the Math. So first and foremost, let's actually talk about misconceptions and the misconstrued facts that media portrayed in its announcement. First of all, this is not a new system. We knew about TRAPPIST-1 since March of 2016. The same person who published a Nature paper just recently found this system using a telescope in Chile, and this particular system is located 39 light years away from us. We're going to go to it right now in Space Engine by typing TRAPPIST-1 right there. So let's fly to it. It's approximately 39.4 or 0.5 light years away from us, and it's a very dim, ultra cool red dwarf that is practically impossible to see. You would not be able to see this with a telescope at home. You would need to have a very specialized infrared telescope that only scientists have to be able to see this particular star. Now, this is what the star might look like, and we're going to accelerate time just so you can see how it spins around as well. Now, what is so special about the star? Well, first of all, it's actually not very massive. As a matter of fact, its mass is on the border of being the lightest possible star. This might actually be one of the lightest stars we've ever discovered. It's only about 8% of the mass of our own sun. Now, on top of that, since this is such a cool star, as in like very cold star, it doesn't produce very much heat, so its actual habitable zone, as you'll see when I show it to you in NASA's Eyes, another software that I'll be using, is actually very close to it. It's essentially not too far away from where it's located. Now you can see there's like at least 2 planets orbiting around it already, and if I zoom out you'll see the third one right there. These are the planets we discovered in 2016, so this is TRAPPIST-1C, TRAPPIST-1b, and TRAPPIST-1d. We thought there were 3 planets, so we decided to take a look at this particular system for slightly longer, for 3 weeks specifically, using various telescopes. And what the scientists discovered is that yes, these 2 planets are there, but that particular planet is actually not just one world. It turns out that this is actually 3 different worlds. And then they also found 2 more planets. In other words, this system now has 7 registered planets, all of them relatively similar in mass to our planet Earth. Now, this is what Space Engine simulates these planets as. It shows them as ridiculously cold, very dark worlds, covered in, you can see Aurora here, covered in super highly energized particles that are striking the surface of these planets from this red dwarf. Now, there's a video I'm going to be posting about why red dwarfs actually make one of the worst possible stars to find life around. In other words, I can tell you right now, even if we go to this star system, the chance for us to find either atmosphere or life on these planets is going to be very low. You're going to find out why very soon when you watch the other video I'm going to be posting. I don't want to spoil just yet. But let's not spoil the fun. Let's actually maybe land here and see what the surface of this particular planet looks like. There's a bit of an atmosphere here, but not too much. And the temperature here is very cold, minus 230 degrees Celsius. Now that's according to Space Engine. We might have actually underestimated how much heat this star produces because it's very likely it's a little bit warmer here. Let's go to TRAPPIST-1C, which is right there, and see what that planet looks like as well. And then we're going to also go to the other simulation, and I'm going to show you the much more realistic representation of these planets that NASA created, but they're not going to look as beautiful as they do in Space Engine. So we're going to just have to wait for the new version of Space Engine to come out before we can actually imagine these beautiful planets in all of their glory. Now, the thing about stars that are red dwarfs and planets around them is that usually all of these planets are tidally locked. In other words, the same face will always be facing the sun or the star. If I were to zoom out here, you would notice that as this planet orbits around its parent star, it's always the same side that's facing it. This is unfortunately a problem for life. This is a problem for evolution. This is a problem for habitability of a planet. If the same side always faces the star, it means that one side is always very, very hot, one side is always very, very cold, and you can only find area with potentially liquid water right in here, twilight zone, the twilight area, because here is going to evaporate, here is going to freeze, here is going to be kind of okay. So all of these planets will look very, very different from what we kind of imagine as planets today. So that was B. Let's actually take a look at C as well. C will look very, very similar. And so that's the system that we discovered, and this is the system that is creating so much excitement now. Now, 39 light years away is pretty far, but not far in terms of stellar distances. It's about 10 times as far as the closest star to us, Proxima Centauri, that has Proxima b, Earth-like planet. But all in all, it's actually reachable. If we're going to be able to reach Proxima Centauri one day, we might as well just come here instead, because this obviously has a lot more interesting stuff orbiting around it. So as you can see, this planet is also tidally locked, unfortunately, and so every time it orbits around its star, the same side always faces the star. Alright, so now let's actually go to NASA's Eyes on Exoplanets, its own sort of proprietary free software that you can totally download from NASA's website as well, and take a look at how they visualize this particular system. So, first of all, we're going to go to the system. Oh, actually, we're going to click right here. Look at this. System with 7 Earth-sized planets. We're going to go to the system directly, and we're going to take a look at what all of this is going to appear as. So here is the system of TRAPPIST-1. Now, the interesting thing about it, so if you look at the habitable zone, you'll notice that 3 of these planets are technically in the habitable zone of TRAPPIST-1. Now, in comparison to our own solar system, though, this is actually really, really close to the star, which creates a bit of a problem, as I mentioned before. So let's actually compare this to the solar system, and you'll see that Mercury is right there. It's very, very far away from the actual star that we have in the middle. Earth is obviously far, far away as well. So the farthest star here is so much closer to its parent star than Earth is to the sun. And this is because TRAPPIST-1 is actually a very, very, very cold, very small, not at all massive star compared to our sun. Now, the star itself is not very cold, and it's so dim, as a matter of fact, that it will be invisible to the naked eye. And even if you use a very powerful telescope, as I mentioned before, you would not be able to see it. Its total brightness is 18.8, if you know what this means, but basically it's very, very dim. And this is known as a super cool dwarf. Super cool, not because it's so cool that it has 7 planets around it, but because it's actually that cold. Its temperature is just over 2200 degrees Celsius. But because this is a red dwarf, what we know about red dwarfs is that they live for a very, very long time. This star is going to live for at least 4 to 5 trillion years. That's like 1,000 times longer than our sun. So, you know, if we one day settle on one of these planets and they become habitable, then that means that humanity can live here for a much longer time than we would be able to survive in our own solar system. So, we have 7 planets here. Let's take a look at the visualization or visual representation of these planets in Eyes on Exoplanets, because they look pretty cool here. So, we're going to go to Planetary View, and we're going to click on TRAPPIST-1b first. This is the closest planet not in the habitable zone. So this one is a little bit too hot for comfort. And as you can see, it's represented as a kind of a hot lava-like world. It's about 85% mass of Earth. Now, this is actually a mistake. It's not 8.5%, it's 85%. And so, all in all, it's relatively similar to Earth. Planet. Its radius is a little bit larger, meaning that it's probably not as dense as Earth, which also suggests that it lacks the magnetosphere needed to protect it from the super, super highly energized particles coming from the star. Next on the list is TRAPPIST-1c. And this particular planet is about 1.4 1.38 masses of the Earth, and it's relatively similar in radius. So this suggests that maybe, just maybe, this planet does have a lot of iron on the inside and has a strong magnetosphere. And if it does have a magnetosphere, it might be able to protect itself from the star. And as you can see, it's represented here as a kind of a liquidy greenish world. But all of this is, of course, just a visual representation. It might look completely different. It might not even have any of this. And we think that it's very likely going to have an ice cap here on the other side, because all of this is characteristics of planets that essentially have tidally locked orbits. So as you can see, it's sort of always facing away from the star in this particular region. All right, next one is TRAPPIST-1d, and this one is going to look very, very cool. So this is right in the middle of the habitable zone in this system, and this is what it looks like. So here, it's only about 0.4 mass of Earth, but it's about 0.77 radius of Earth. And the water shown here, as you can see, is hypothetical. So maybe it's there, maybe it's not. For the most part, though, the side facing the star is completely dried out. It's totally dry. There's an occasional lake here and there. There's water on the twilight area, and then there's ice on the dark side. And the next planet, TRAPPIST-1e, will have very, very similar features, but it has slightly different parameters. It's about 62% mass of Earth, and it's about 0.9% radius of Earth. So here we seem to have more water, and this is once again just an artistic representation. It might look completely different, but of course, because there's water, there's also ice on the other side. And if I accelerate time here just to show you what it looks like, this is what it's going to look like when it orbits around its parent star. So it's always facing the sun, the star, using the same side. And TRAPPIST-1f looks very, very similar, maybe a little bit colder because it's slightly farther away. The mass here is 68% mass of Earth, and the radius is slightly larger than Earth. And you can usually tell that because mass is smaller than Earth and the radius is bigger, this means that density on this planet is much lower, which suggests that it's very likely similar to Mars in that it has less iron and less metal on the inside, which also suggests that it might not have magnetosphere needed for life to survive on this particular planet, unless of course it's underneath the ice shelf. 1G and 1H are not going to be in the habitable zone, and so 1G here is represented in a very, very unusual way. It is a terrestrial planet with the masses of about 1.3 masses of Earth and a radius of about 1.13 radii of Earth, but it looks very, very gas giant-like. Now this is once again artistic representation of what it may or may not look like, but here you go. So this is what it might appear as, and because of the mass to radius ratio, you can kind of assume that it also has a lot of metal on the inside, so very likely also has some sort of a magnetosphere protecting the surface of that planet. The last one is TRAPPIST-1h. We don't really know the mass of this particular object, but we know that its radius is about 75% radius of our own planet, and we think that it's probably just a frozen ball of ice. Kind of looks like this. And so that's essentially the 7 planets we've discovered. And it's mostly exciting because all of them are very, very similar to Earth in terms of mass. They seem to be, or at least half of them seem to be orbiting in the habitable zone, so that's where you can potentially have liquid water. But because this is a red dwarf, and because we know red dwarfs are very, very, very unpredictable in terms of emissions and flares, and because they tend to release a lot of very powerful particles, a lot of X-rays, a lot of really, really destructive emissions that can actually strip the planets of the atmosphere, this still means that maybe all 7 of these planets actually don't have any atmosphere, don't have any water on them, and might actually be just rocks orbiting in space. One day maybe we'll be able to see them in more detail, but for now that's all we know about them, and that's all we've discovered. And not to spoil the fun, but there's actually quite a lot of other things that might actually prevent these planets from having life on them. One of them is that because they're so close together, as a matter of fact, if you were to actually stand on this planet and look into the sky, you'd probably see objects size of our moon or even larger than our moon orbiting around you, or orbiting close to you, that is. all of these objects would be causing some huge tidal effects on each other. And this, of course, means that there's a lot of volcanic eruptions on these planets caused both by the star and the other planets around in the system. So these planets are probably very hot on the inside and constantly cause each other a lot of problems via tidal effects. So even though Universe Sandbox Square already has a huge database of various planets, various systems, and various stars, and also exoplanets as well, it doesn't yet have the newly discovered TRAPPIST-1 system created, so we need to make our own from scratch. We do have the TRAPPIST-1 star, however, which we can actually add by typing TRAPPIST here, and it will show up right away. We're going to place it. It's listed as a red dwarf type M8. And it does have a relatively accurate parameters here. So basically it is about 83.8 masses of Jupiter. It's essentially just a little bit bigger than Jupiter in terms of the size. So this is what Jupiter would look like. But it's much more massive. It's 84 times more massive than Jupiter. So it is a star. It's not a brown dwarf. It's an actual ultra cool star, as in very cold, not that it's super cool. And its surface temperature here, it's about 2500 degrees Kelvin, although I think in reality it's a little bit lower. Now, to add all of the planets that we've discovered last year, we can just click on this Add Planet to Stars. And there you go. There's 3 planets that have been added to the TRAPPIST system. You'll notice that they're actually orbiting very funny. It's because their inclination has been discovered to be about 89 degrees in comparison to our own system. So there is the inclination for all of these 3 planets. TRAPPIST-1b, TRAPPIST-1c are too close to the star, so they're very likely actually outside of the habitable zone. Whereas TRAPPIST-1d, turns out that it's not just one planet, but it's actually at least 3 separate objects. So let's create this from scratch. These 2 are already with relatively accurate parameters. We're just going to double check that their masses are actually correct. And we're going to do this using the parameters available to you for free on a website known as TRAPPIST-1. It's a website set up just specifically for this particular system. So TRAPPIST-1b, which is the planet that we have right here, is very likely a very hot world with about 0.85 masses of Earth, 1.1 radius of Earth, much lower density or slightly lower density than Earth, and thus lower density than Mercury, which also suggests that it's probably mostly rock, not as much metal, and it's very unlikely that it has any water on the surface as well, because it's a little bit too close to the parent star. It's also tidally locked, so one side is always facing the star. And so one side is always very hot, and the other side is probably very cold. And a single orbit here takes only I think it's 1.5 days, let's double check. 1.51 days. It's slightly eccentric with about 8% eccentricity, similar to some of the planets in our solar system as well. And all of the inclinations for all of these planets here will be about 89.4 degrees. Oh, and one thing I forgot to mention is how close is it to the actual star. So the distance here is about 0.011 astronomical units, which is essentially 11% of the distance of Earth to the Sun. So it's much closer to the star than Mercury. TRAPPIST-1c, the next planet, is also going to be very hot. And it's also tidally locked to the TRAPPIST star. And here, what makes this particular planet different and kind of interesting is that it actually has relatively high density. So the temperature here is, according to the simulation, is currently 67 degrees Celsius. So it's a little bit hotter than what you would want it to be, and possibly even more hot if there's any atmosphere on the surface. But this is definitely not going to be a very easy world to inhabit, but there's some really cool things about it. First of all, it's about 1.38 masses of Earth, so it's more massive than Earth. It's a little bit larger than Earth, and it's a little bit more dense than Earth. This suggests that it actually has very high metal content on the inside. And this, of course, suggests that this particular planet might actually exhibit a very powerful magnetosphere. In other words, it might actually be protected from the star that it orbits by a very powerful magnetosphere that's generated inside the planet. Now, what this means is that maybe, just maybe, there is actually some kind of boiling water on the surface. There's also possibly some sort of an atmosphere here. So let's just add a little bit of atmosphere to it. But if there is atmosphere, this also suggests that there might be actually quite a lot of greenhouse effect, making this planet even hotter. So it might be as hot as 100 degrees Celsius or the temperature of boiling water. So TRAPPIST-1c, despite being so exciting in terms of other parameters, including, of course, its orbital parameters of 2.42 days, eccentricity of about 8%, and essentially being relatively close to the star but not close enough to be extremely hot, it still is very likely just outside of the habitable zone, still in the very hot region of this solar system. Now, TRAPPIST-1d and 1e are a little bit more exciting. First, let's look at TRAPPIST-1d. Now, this one is also very likely tidally locked, so we're going to tidally lock it. But as you can see, it already has a bit of liquid water. The problem is that it's possible that it doesn't have enough iron, and the reason we know that is because even though its mass is about 0.4 masses of Earth and its radius is about 0.7 radius of Earth, its density is lower than Earth. So there might not be enough iron, enough metal on the inside to circulate to create the magnetosphere. If there is no magnetosphere, this suggests there is no atmosphere and also suggests that there is no water. Whether there is water here or not, maybe one day we'll discover by using other telescopes, but for now we can assume that there is no water simply because the magnetosphere is not present to protect this planet from various flare eruptions that TRAPPIST-1, which is a star of course, would often exhibit. So this is TRAPPIST-1d, and if you want to take a look at its orbital parameters, its semi-axis or its distance to the star is about 0.02 astronomical units, its eccentricity is 7%, and its orbital period, or 1 year here, is about 3.93 days, or basically close to about 4 days. Now, the next two planets in the TRAPPIST system are kind of exciting, mostly because they're located pretty much in the middle of the habitable zone, also known as the Goldilocks zone. This is where you would expect to have liquid water. Now, TRAPPIST-1e, let's look at its parameters. So its mass is about 0.6 masses of our Earth, and its radius is about 0.9%, or about, sorry, 92% radius of our Earth. In comparison to Earth, this is what it looks like. So in terms of size and mass, it's similar, but it's less dense. This once again suggests that maybe, just maybe, the magnetosphere here, if it exists, is not very strong. So if it does exist, though, it might protect this planet from the powerful streams of various ionized particles that are coming from TRAPPIST, and thus create some sort of a atmosphere that might be able to actually support liquid water and, of course, thick atmosphere on the surface of this planet. But we don't really know if this is true, and we won't really find out for quite a while. But let's just add water just for fun to imagine that it's going to be a water world. However, the temperature here is relatively cold, and that's because we just didn't create enough greenhouse effect for this planet just yet. Now, this one is actually probably one of the best chances for us to find any kind of habitable world in this system, mostly because it's just in the right region, but it's still maybe a little bit too small to have a powerful magnetosphere to protect it from the star. TRAPPIST-1f, very similarly, is actually, oh, look at the temperature, very, very warm, but I think it might actually be falling over time. Anyway, so the parameters here are about 0.68 masses of our Earth. It's a little bit larger than Earth in terms of radius, so it's clearly a lot less dense. And once again, this means that there's less metal on the inside, less magnetosphere, and so liquid water might actually be just a science fiction in this case. There might be nothing on the surface. And it even might not even have any atmosphere, even though I decided to create some here. The reality might be this. It might be actually completely free of atmosphere, simply because, once again, the powerful streams of different flare emissions from TRAPPIST-1 would strip this planet entirely of all of the atmosphere. It will be absolutely empty. However, maybe on the opposite side of the planet, there might be some ice and stuff that accumulates over time. But we wouldn't be able to survive there because it's just a little bit too cold. And don't forget, all of these planets are actually tidally locked to the star. So all of them have very similar parameters and very similar features on the surface. Basically, every single one of these planets will have very dry, very sort of hot environment here, possibly completely scorched in some cases. Then there is going to be the twilight area that's going to possibly have liquid water, but very unlikely. And then there's going to be the dark side that's always in the dark, always frozen, always super cold. So all 7 of these planets will have these because we are pretty certain, like 99% certain, that they're all tidally locked. Alright, so this was 1F. Then we have the planet 1G, which is a little bit farther away, but still in the relatively habitable area. And so here, this actually might be another very interesting planet. The reason why it's interesting is that its radius is about 1.12 radii of Earth, and its mass is about 1.34 masses of Earth. So this particular planet is quite as dense as, let's say, Venus. This suggests that maybe it has liquid iron core. So this might be actually all this liquid iron core on the inside. And this also might suggest that there is a magnetosphere. So we're going to give this planet a magnetosphere, but there is a problem, of course, and the problem is that even if there is a magnetosphere here, this planet is a little bit too far from the TRAPPIST-1 star to actually have enough temperature to maintain liquid water. So it's possible that here everything is going to be basically kind of frozen-ish. I'm going to give it some water. Actually, a lot of water, but as you can see, it's all going to be frozen, even if I give it quite a lot of atmosphere. Let's actually give it like really thick atmosphere that we're going to assume is going to survive the hostility of the parent star, despite it being the red dwarf that usually has a lot of flare emissions. One just actually happened. You kind of saw it erupting from that side right there. So, even with the thick atmosphere, it's very likely it's not going to be warm enough. We're going to wait a little bit, but I don't think it's going to warm up enough. Well, actually, never mind. I spoke too soon. It totally has enough temperature or enough greenhouse effect to warm up quite dramatically and to melt this liquid water here. But the problem is that this is with 3 pressures of atmosphere. In other words, 3 times the atmosphere on the surface of our planet Earth. To maintain this atmosphere, this planet has to have a really powerful magnetosphere. The magnetosphere here has to be more powerful than on Earth because otherwise the TRAPPIST-1 system, or TRAPPIST-1 star, would actually strip everything from the surface here. So let's just assume that maybe it does have magnetosphere and maybe there's water. So this would be actually one of the better opportunities for us to find a new home outside of our solar system. And lastly, we have TRAPPIST-1H, and this planet is actually kind of far away from everything, so it's very likely to be just an ice ball if there's water, or to be just a very cold non-ice ball if there's no water. And the parameters here are, we don't really know its mass, but we know that it's about 0.75 radii of Earth. We don't really know its density, but we know that it orbits the star every 20 days. And the distance from the star is about 0.063 astronomical units. And you can see this under here. So this is about 9,431,800 kilometers in distance. So this is probably not a habitable world, but nevertheless, it's an Earth-like planet as well. So, of all of these planets, let's actually see which one has the highest Earth similarity. So this parameter right here. So TRAPPIST-1H is 0.63, TRAPPIST-1G is 0.914 with about 19% chance for life, TRAPPIST-1F 0.6862, 0.92, and look at that, 44% chance of life on TRAPPIST-1E. This is right in the middle of the habitable zone. 1D has a 0.9 similarity, 0.694 for TRAPPIST-1C, and the last one is 0.77. So many of these planets are very similar to Earth, so it really all depends on the magnetosphere. If there's magnetosphere, chances for life and liquid water in the atmosphere are very high. If there is no magnetosphere, chances are very low. Now, one thing I want to mention before actually finishing this video is the idea of temperature equilibrium. This is essentially a principle where if I were to put a planet somewhere right here, let's say we'll put Mercury, what would be the actual temperature, assuming that this body does not have atmosphere, does not have any greenhouse effect? What would be the temperature on the surface if it basically receives all of the starlight from the sun, from its star? Now for Earth, that equilibrium is about 260 degrees Kelvin. The actual temperature on Earth, though, is much warmer. It's about 35 degrees warmer, meaning that the greenhouse plays a very important role. So for all of these planets, we were actually able to find this equilibrium temperature, and there is a bit of a speculation we can make about them. So for TRAPPIST-1b, that temperature is too high, which means that this planet is ridiculously hot. So is this one. This planet is very likely going to be very hot because even without the greenhouse effect, the temperature here, the equilibrium temperature is 340 degrees Kelvin, which is close to about 70 or over 70 degrees Celsius. So it's going to be very toasty to live here. TRAPPIST-1d, however, and the other next one, TRAPPIST-1e, have very comfortable temperatures. Here it's 288 degrees, which is very close to 260 on our planet Earth. And here it's about 251, which is slightly below Earth's 260. So if these two planets here have atmosphere, and if these two planets have magnetosphere, they're not only going to be habitable, but they're also going to be very, very, very strong candidates for us to find life on them. These two planets are very important. Now, TRAPPIST-1f and TRAPPIST-1g have slightly lower temperatures of 219 and 198 Kelvin, meaning that they need to have very strong atmosphere on top of the magnetosphere to actually be candidates. And, well, that's really it. That's all I wanted to do in this video. I wanted to create TRAPPIST system. I wanted to talk about various properties and various parameters that we've discovered. And also, I'm going to show you where it's actually located in relation to our star. If we go right here into nearest 100 stars, we're going to open the simulation that has essentially all of the nearest stars near us, and about 15% of them are actually these ultra cool dwarfs similar to TRAPPIST-1. If you look around long enough, you might actually be able to spot it because it's not very far from us. It's only about 39 light years away. So let's look for it right now. And so at a distance of about 39 light years away, there it is. You can kind of see it right here. This is actually a manually placed star because I just realized this particular simulation has not been updated since 2012, so you might not be able to find it here, but I wanted to put the star in there just to give a comparison to some of the other stars in terms of the actual distance. So here's the infamous Alpha Centauri with the Proxima Centauri right next to it, right there. This is the other red dwarf that was the center of attention last year when we discovered another Earth-like planet known as Proxima b around it. This is about 4.2 light years away, and that's about 39. It's about 10 times as far. But nevertheless, that's still pretty close in terms of space distances. Anyway, that's really all I wanted to talk about in this video, and hopefully you enjoyed it, and hopefully now you know what TRAPPIST looks like. Hopefully you've discovered a little bit more about this fascinating system, and now you know what we might discover there one day as well. So, with the 2017 discovery of TRAPPIST-1 system and its 7 Earth-like planets, people started to basically be fascinated by the idea of these being Earth-like planets with essentially similar composition and similar structure to Earth. But of course, that is not the truth, because every single one of these 7 planets is very, very likely, almost 99% certain, tidally locked to their parent star. In other words, the side that's facing the sun is going to be very hot. The side that's facing away from the sun or the star is going to be very, very cold. And then only right here on the twilight area, the so-called twilight zone, is where you might find some liquid water and possibly, just possibly, potentially some life. Now, so why exactly do we know that this happens, and why exactly does this happen? So let's actually discuss this using something a little bit more familiar to us. Specifically, we're going to be looking at the system of Jupiter. And so here we are around Jupiter with all of its moons orbiting around it. There's quite a lot of them, but the ones we'll be looking at are only the moons that basically have been with Jupiter for a very, very long time. Specifically, of course, the so-called Galilean moons, Io, Ganymede, Europa, and where's the other one? Callisto. There you go. So these 4 moons, they have been with Jupiter for a very, very long time, and these are the moons that essentially have been here since the creation. Now, why only these moons? Well, because it's these moons that we actually are going to use to simulate the tidal lock, and of course to try to understand how tidal locking occurs. So let's just look at Io. Io is the closest, and as you can see, it is also tidally locked to Jupiter. So I'm going to show you that it's always the same side of Io that's going to be facing away from it. So look at this spot right here. You'll notice that it's always facing away from Jupiter. Every single moon of Jupiter has that. If I go to Europa, it will have the same thing. It's always the same spot that's going to be facing Jupiter, for example. So let's just maybe do it from this angle right here. And you'll notice that as we're orbiting around Jupiter, it's actually the same side that's always facing Jupiter. And there's another way of checking these by going under motion and looking at the rotation period and then comparing it to the orbital period, which is somewhere right here. And you'll see that it's exactly the same number, or almost the same number in this case, because I think it might have changed just a little bit due to the simulation constraints here. So Ganymede has the same, of course, and here we have 715 days rotation period and 716 orbital period. And lastly, Callisto, which is the farthest away from Jupiter, has the same parameters. So it's 16.7 rotational period and 16.7 orbital period. Unfortunately, Callisto, though, is kind of invisible right now. I don't know why it's hard to see, but the I'm guessing it's because the sun is not present here. But we don't really need Callisto for this experiment, so let's just focus on Io, Ganymede, and Europa. So what exactly is tidal locking and how does it occur? Well, tidal locking is also known as gravitational locking, and it occurs over the course of an orbit, usually over a period of a long time. And essentially what it does is it reduces the transfer of angular momentum between two objects. When two objects are spinning, they create a bit of a momentum. But over time, between two astronomical bodies, the gravitational partner of one object will try to neutralize this momentum and essentially cause two objects to start orbiting as fast as they're rotating. So for example, if I were to place, let's just say Mercury right here, it would not be gravitationally locked, or it would not be tidally locked to Jupiter. So right now it's experiencing a little bit less tidal stress on the outer side than it does on the inner side. This gravitational stress is usually caused by the torque force, or by basically torque applied by the gravity of Jupiter in this case, to the gravitational or tidal bulges created on the second object. So it's essentially represented really well in the picture right here, where you can see that what happens over time is that the tidal forces try to align with the bulge here, and basically we're trying to neutralize the forces caused by the tidal effects. Now, we know for a fact that this is exactly what happened to our moon. So over time, after the creation of the moon, our moon essentially neutralized the tidal effects that were caused to it by Earth, and became tidally locked to our planet Earth, essentially always facing the same direction. Earth, on the other hand, slowed down over time. So our day used to be much, much longer. As a matter of fact, when the Earth was just created, our day was about 6 hours long. Now it's 24 hours long. So the Earth slowed down about 4 times. And eventually it will also become tidally locked to the moon. It just will take several billion years. But, you know, by then Earth will very likely disappear due to the expansion of our star, the Sun. But that's another story. Anyway, so tidal locks happen quite often and quite a lot. One of the more common objects that has a dual tidal lock is actually Pluto and Charon. And so in the case of Pluto and Charon, you can see that they're actually tidally locked to each other, and that's mostly because their masses are relatively similar and they're relatively close to each other. But when one object is much more massive than the other, smaller object will be tidally locked, but the larger object usually will not be tidally locked. So this is one of the reasons why, in case of Jupiter, Saturn, and other large planets, their satellites are tidally locked, but the planets themselves are not tidally locked to anything. So, from this, what can we actually speculate? Well, first of all, let's just say we multiply the system of Jupiter, in terms of mass at least, by about 80 times. In other words, we're going to turn Jupiter into similar mass object to TRAPPIST-1. So it's going to become approximately 80 masses of Jupiter, and right away it actually turns into some sort of a super cool dwarf star. Now let's actually position these objects so that they actually start orbiting around our new Jupiter. And we really are only going to keep the 4 Galilean moons. Everything else can just kind of fall into Jupiter and disappear. Now let's actually also change their mass as well, multiplying it by about 80 times. So they will essentially turn into planets of this newly formed star, the Jupiter, or this really cool dark dwarf star called Jupiter. Also, we might as well give it a little bit more temperature than that, because it's currently a little bit too cold here. The current temperature of this object is only 122 Kelvin. The reality is that it's about 2200 Kelvin, so there we go. And I think this might actually start burning some of our planets. That's not good. But anyway, so let's start with Io. Io is going to place at a slightly farther away distance from this star, mostly because otherwise it's going to get destroyed pretty quickly by tidal forces. We're going to place Io at about 0.01 astronomical units from the star, which is going to be the orbital period of about 1.5 days. So it's just a little bit farther away from where it used to be, and basically even closer than the orbit of Callisto. So all of the other objects will basically kind of get very similar parameters here. This will be orbiting around 2 days, and the other ones at around 2, 4, and let's just say 8 days. So there's our new system. Let's also give them a little bit more mass just to make them more planetary-like. So let's actually just multiply their mass by about a factor of 80 as well, just to make this a little bit more realistic. So this here will become about half the mass of Earth. This here will become just a little bit over half mass of Earth, and the other objects will become even a little bit more massive. So this is 1.5 masses of Earth, and this here will be about 2 masses of Earth. So as you can see, multiplying all of this by about 80 will create something very similar to the system of TRAPPIST. The distances don't have to change very much, but the idea here is that the ratio between mass of Jupiter and mass of its original satellites is very similar to the mass of TRAPPIST-1 and TRAPPIST planets. So the effects that Jupiter causes on its moons is actually very similar to the effects that we would expect TRAPPIST-1 star to cause on its planets. So those planets will actually receive exactly the same tidal effects, or very similar tidal effects, as the moons of Jupiter get from Jupiter. So of course this implies one thing, and the implication here is that the model for TRAPPIST is essentially in our own solar system, and that's of course Jupiter that I've just created here. So that model is a pretty good indication that all of these planets, all of the TRAPPIST planets, will be similarly locked to TRAPPIST itself, just in the same way that, if I were to go back to Jupiter here, in the same way that all of these moons, including Io, Ganymede, Callisto, and Europa, are locked to Jupiter. So here, the same side always faces the gas giant. If I go to Saturn, for example, even the farthest moon, Titan, is going to still be tidally locked. So here, even though it's kind of hard to see what side is facing what, because Titan's surface is very difficult to see, we can actually go in here and remove all of this. We can actually go under motion here and look at the actual numbers. So rotational period is 15.9 days, and the orbital period is also 15.9 days, implying that this moon is also tidally locked to Saturn. So all of the major moons around gas giants and around ice giants, as long as they started there from scratch, from the beginning, from the formation of the system, essentially are tidally locked. The only few moons that are not tidally locked are, for example, Neptune has this moon called Triton that seems to orbit against the flow and is not tidally locked because it's doing its own thing. And that's because we think that Triton was long ago captured as a passing rogue dwarf planet by Neptune. And we also are pretty sure that through interaction of tidal forces, it will one day collide with Neptune and will very likely disappear from existence. And so all of this hopefully gave you a pretty good idea that in general, we are very, very certain that TRAPPIST planets are tidally locked to TRAPPIST-1, and this also applies to other red dwarf systems that we've discovered, including the infamous Proxima b right here, where we are almost 100% certain that Proxima b is also tidally locked to Proxima Centauri. So all of these planets orbiting around red dwarfs or super cool dwarfs or any small stars like Proxima Centauri or any of the other stars around our sun that are red dwarfs, like for example this one right here, LHS 3003, this one right here, Wolf 1061. We're pretty sure they have planets around them, but those planets will very likely also be tidally locked, including of course the planets of Barnard star, one of the earliest stars we've discovered that were actually a red dwarf. And so anyway, so that's all I wanted to talk about in this video, and hopefully you learned something from it, and hopefully now you know why we're certain that TRAPPIST planets are tidally locked and what it actually means to us later on, and how we can actually use our own solar system to model all of these tidal locks by using systems like Jupiter and Saturn and looking at them in a little bit more detail and trying to figure out what exactly we can learn from the interaction of Jupiter and its moons, and can then compare them to smaller stars like brown dwarfs and red dwarfs as well. Now, so what I wanted to do in this video is basically erase all of the TRAPPIST planets, which are kind of Earth-like, but not really Earth-like. And of course replace them with the most Earth-like planet we know. Everything here will become Earth. And we're going to see how our new 7 Earths will perform in this TRAPPIST-1 system. We're also going to talk about sciences and various effects here that will make life in the system very difficult. But let's just start by placing them first. TRAPPIST-1b, your orbit is about 151 days, and I believe the eccentricity here should be about 8%, and also the inclination should be about 89%, but we're going to ignore inclination because it won't really change anything. So let's remove TRAPPIST-1b, and let's now place our beautiful planet Earth as the first contender in this new system. And let's maybe name them as well, just so we'll remember which planet is what. So this will be Earth B. Then we're going to place Earth C right here, where TRAPPIST-1c is, with the orbital period of 242 days. So let me just skip this part, and I'll just place all of these new Earths manually by changing their orbital parameters and of course their names as well. Next is TRAPPIST-1d, E, F, G, H, and here we go. So A, B, C, D, E, F, G, H, all of them in the exactly same position as the original planets of TRAPPIST system. And anyway, so here we go. We have 7 Earths in the orbit. I'm going to actually remove the orbits for now. C and B are a little bit too close to TRAPPIST, so it's very likely that there's going to be no liquid water left, but we'll see in a few minutes. D, E, F, and G are very likely going to have some liquid water because they're sort of within the green habitable zone. And then H possibly will have frozen water because it's too far away from the star. So let's actually run the simulation for, I don't know, like a few years or something, and just look at the temperature go down. That's pretty crazy. And let's see what actually happens to our beautiful 7 Earths that orbit the TRAPPIST system now. So I'm going to just kind of make this simulation run itself for a while. And we also might be able to see some of the interaction between the planets because they're relatively close to each other, which means that they might start pulling on each other and create all kinds of different synchronicities. In reality, TRAPPIST-1 system has a lot of tidal locks, but also has a lot of resonances between these planets. So they actually are always in some kind of a resonance with each other. I obviously place these very randomly, so there's no resonance whatsoever here. But we might discover some later on. Anyway, so looks like the temperature on Earth H is still dropping, but it's already quite a visible ice ball. It's basically too cold here for water, and it's going to be a really, really, really cold ball of ice. Also, it's much farther away than the other planets, so one orbit here is about 20 days, meaning that it's very likely that it also spins much slower. So if I were to tidally lock this particular object by pressing this button right here, you would see that one day here would be 20 days long. This also implies that one side would always be facing the sun, and this side right here would eventually get really hot, and there might be some liquid water on the outskirts where it's not as hot, and most of the planet would be covered completely in ice. So that's Earth H. Definitely not going to be a very habitable place. Earth G is sort of within the habitable zone, and the temperature here is still very cold. And that's actually a lot colder than I thought it would be. Now, this is because the greenhouse effect here didn't really do much. The actual greenhouse effect due to the atmosphere on our planet is usually about 32 to 33 degrees Celsius, or just degrees in general. And here our temperature, even if we were to increase the greenhouse effect, is still kind of too low, and it's still actually dropping. So this might even be lower than that. So Earth G is also not a very nice place, unless of course it has more atmosphere. If it has more atmosphere and more greenhouse effect, in that case, it might actually have liquid water, but for now, it is a frozen world. And because it's also tidally locked, which I should do right now, it's going to have one side that's a little bit too toasty. Let's go to Earth F, and look at that. This one is also very cold. What is going on here? Now, this is very interesting. So, even though all of these planets are actually in the habitable zone, these Earths in Universe Sandbox seem to be a little bit too chilly. They don't seem to get enough energy from TRAPPIST-1. Now, I'm starting to wonder if maybe it's because of other factors, like albedo effect maybe. Although that albedo of 0.32 implies that the majority of light on our planet is actually absorbed. And I'm not entirely sure what's happening here, but I just realized that there seems to be occasional eclipse going on around this particular planet. And let's see if this is actually what's happening here, because I think I just witnessed a shadow passing by, and I'm guessing it's because of another planet passing in front of us. And so we might actually witness one of those occultations or one of those eclipses in a few seconds right now, actually. Let's see if this is what's happening. So there is Earth B passing in front of the TRAPPIST right now, and nothing. Oh, there we go. Look at that. That was a huge shadow. That was definitely a huge shadow from Earth B. Wow, that's awesome. So on this particular planet, you would be experiencing 1, 2, 3, 4, at least 4 different eclipses once in a while when the other planets come in front of the star. On Earth H, however, that's 6 different eclipses. That's a lot of eclipses. Anyway, let's move on to the next Earth. In this case, it's the one down in the alphabet, Earth E. And once again, a little bit too cold, but maybe not as cold as the other objects. So here the temperature is minus 17 degrees Celsius. Lots of eclipses. Look at that. I should probably also make this tidally locked just to make it more realistic. And now we tidally locked our planet to basically make North America ridiculously hot. So North America is going to be always facing the sun now. But as you can see, the temperature here is cold, and it's still falling. It's falling even lower. So that's not a good sign either. That means that so far none of these Earths, plural of Earth, have actually been warm enough or became warm enough to be habitable. Except for Earth D. Look at that. Beautiful blue world. Is the temperature stable? Yeah, it's a stable 18.4 degrees. That is amazing. Okay, so let's once again tidally lock this. And now I've actually tidally locked Australia, Southeast Asia, and Asia in general. And we seem to have a relatively nice, relatively cool looking world here. 18.3 degrees Celsius. It's just a little bit warmer than Earth on average. As you can see, the caps actually, the ice caps have kind of disappeared, which is not really good. And the temperature is still kind of climbing. But basically, for Earth to have a perfect climate, Earth-like climate, it would have to be located somewhere between D and E. Maybe just a little bit after D. Now I'm guessing Earth C is going to be toasty. And the answer is yes, 68.5 degrees. Look at that. Look at that. Everything here is completely brown. Essentially, all of the vegetation, all of the life has been eliminated from the surface. There's still a little bit of water left, but it's probably all boiling, or at least very, very hot, very steamy. And so this Earth is not a very habitable Earth, although the star from here looks pretty impressive. And the last one is, of course, Earth B, the closest to the star. And here the temperature is over 100 degrees Celsius, over boiling temperature of water. So most of this water is probably boiling hot. It's just ridiculously hot. And it's probably only in liquid form because of the pressure, if there's any water left at all. And now you can actually see some of the continents here, or the continental shelves, that is, because a lot of the water has evaporated from those continents, making them a lot larger. So, which is, of course, very, very, very interesting. Anyway, so, well, looks like only one of these Earths was habitable. And that, of course, is Earth number 3. Specifically, we're here talking about Earth D. So this is the only planet that so far has actually relatively nice conditions for us to live, and actually has green vegetation on the surface, which is, of course, great. Now, the only problem here is that it still is not going to be a world we'll be able to survive on. And there's maybe two main reasons for that. One of those reasons is there might be not any magnetosphere here. Now, we don't really know exactly if any of these planets would have a magnetosphere. Our planet clearly does, and it protects us from pretty much everything. But if there is no magnetosphere here, it's very likely that all of the atmosphere and all of the liquid water would actually be stripped away and disappear completely, which I'm going to do right now by removing all the water. And there you go. This is what this would look like. And there would also be absolutely no atmosphere and also no clouds. There you go. Empty world. Now, the other thing is, even if there is a magnetosphere, it has to be really, really strong. And it has to be strong because we're so close to TRAPPIST. We're very, very close to that star. And this star, just like other red dwarfs, is, as you can see, a little bit active. It has a lot of flares going on. It has a lot of emissions, which makes it a very dangerous star to live around. Those emissions can be very powerful, a lot more powerful than the emissions from our sun, which is actually a very mild star. And every one of those emissions would very likely destroy any possibility for life. It would just kind of strip the surface of the planet from everything. So the only way that Earth D could actually have some kind of a life on it is if this life formed maybe in the shadow right here, where it's kind of warm, not too cold, and basically in this region right here, when we're kind of covered from the sun for the most part, but there's still a bit of a warmth going on, possibly even liquid water. This is where we might have this kind of a twilight area life, twilight life, as I guess you could call it. And other than that, these planets, for the most part, are going to be very, very difficult to survive on. And as this kind of gives you an idea, especially if I look at the chart here, just to show you what each of these planets looks like, and also in comparison to TRAPPIST-1 itself. So there is the star, and there are the planets as well. So most of them are kind of too inhospitable, with the exception of the third planet from the sun, just like in our own solar system. These ones are a little bit too cold. So here we are in our own solar system, and let's actually explore maybe 3 or 4 different possibilities of TRAPPIST-1 being in our solar system. The first possibility is if our sun was actually a dual star with TRAPPIST-1, or a binary star with TRAPPIST-1 as its partner. So we're going to actually decelerate time here a little bit and go under TRAPPIST and basically place it in balanced motion around our sun, maybe around this far. So there you go. They're going to be orbiting around one another. And as they orbit, well, there's going to be a bit of a wobble because they're going to have a barycenter in between them. But I'm also going to actually add planets to TRAPPIST-1. So let's actually add some planets here just so that it actually looks a little bit more realistic. Now I think it doesn't have all the new planets in it yet. Yeah, it only has the old 3 planets. And you'll see that even these 3 planets will actually not stay in this orbit for a very long time. So these 3 planets will very likely disappear pretty quickly, but let's actually see what happens to the rest of our solar system. So we're going to accelerate them just a little bit. and watch what happens to both the TRAPPIST planets and also to Earth. So if these two stars were orbiting around one another that close, it's very unlikely that they would have any planets in a certain radius around them, because they're going to create a lot of, well, essentially gravitational waves. They're basically going to be creating a lot of disturbances that will prevent stable orbits from forming around them. It's going to take a very, very long time for us to actually see if any of the planets are going to have stable orbits. But chances are that the 3 or 4 planets at a farther away distance will be able to stay in this orbit. But Mercury and possibly Venus and maybe even Earth might actually get flung out and fly away. As you can see, Venus has already changed its orbit, so did Earth, acquiring a very different orbit from before with changing eccentricity and also changing semi-major axes. As you can see, its orbit is not as stable as it used to be. But unfortunately, the TRAPPIST planets are gone, except for maybe this one that seems to be coming back because it also has a very eccentric orbit. Alright, so that's simulation number 1. Not maybe as fun as I hoped it would be, and mostly because all of the other planets have disappeared. Let's try this again, but this time put the TRAPPIST star a little bit farther away. Maybe this time in between Sun and Mercury. And so here we go, 7 planets and TRAPPIST-1 itself. Let's see if any of them actually do survive this, and if any of them stay in a stable orbit around the binary star that is Sun TRAPPIST. We're actually going to just use the trails here, accelerate time a little bit more, and watch all of them basically fly away into the abyss. That's mostly because there's a lot of gravitational interactions between the Sun and, of course, other planets. And chances are most of these planets will just become the planets of the Sun now, not really TRAPPIST-1. But TRAPPIST still has at least 3 planets orbiting around it, or even 4, I think. Yeah, there's at least 4 planets. We're going to take a look at what they look like in a second. Our own Mercury has unfortunately gained a little bit too much velocity because it passed too close to TRAPPIST-1. So this star right here, TRAPPIST-1, is now going to be actually causing quite a lot of disturbances to the inner terrestrial planets, and there's a very high chance that Venus will also at some point will fly away, and maybe even Earth, especially if they approach this system a little bit closer. And the planets that remained in orbit around TRAPPIST are TRAPPIST-1b, a very nice looking but somewhat hot world with 300 degrees Celsius temperature. TRAPPIST-1c, very similar conditions here. And TRAPPIST-1e was slightly cooler, 276 degrees Celsius, and what seems to be a sign of collision from something. I don't really know what, but something made it collide with something else. It does look really, really cool though. An absolutely brilliant looking planet. Okay. But it looks like, once again, this is not a very stable simulation, so we might need to try this again, and this time place TRAPPIST a little bit farther away. Maybe somewhere where it would most likely be, that is, in the location of the other gas giants. So this time we're going to place TRAPPIST right between Jupiter and Saturn, and then also place its planets as well. And so here's our TRAPPIST system with the 7 planets that are actually in relatively stable orbit, and there is our Sun in the distance. There it is, you can actually see it now because I removed the trails. And so this seems to be a pretty stable system. I'm going to run this for a little bit just to see what's going to happen to our other gas giants. But it may actually look like that I was able to find a location where TRAPPIST hypothetically could actually exist. Now, with time, it will probably cause a little bit of disturbance and cause Jupiter and Saturn to change their orbits a little bit. But for now, though, it has its own system. It definitely has its own planets, and the other planets, specifically the terrestrial planets like Earth, Mars, Venus, and Mercury, are not really affected by this very much because they're a little bit too far away. Now let's actually see if Earth's orbit has been affected at all. We can actually go under here and check the eccentricity and the semi-major axes, and it looks like it's too far away to affect Earth currently. So it doesn't really cause many effects to the inner terrestrial planets, but it might cause a few effects to Jupiter and Saturn. Only time will tell, of course. I can maybe try to see if there's any effect from TRAPPIST by doing the following. I'm gonna remove all of the objects that are actually not needed for us, leave only Jupiter and Saturn and a few other farther away objects, and basically accelerate time now and just kind of see, oh, there we go. That didn't take very long. I was about to say how long it takes for Jupiter and Saturn to change directions, but looks like I was totally wrong. So because TRAPPIST does actually cause a huge gravitational pull on our own sun, the sun will actually change directions, and this is why Jupiter and Saturn will very likely lose direction as well. So I spoke too soon, but the terrestrial planets might actually not be affected by this. They will still be orbiting around the sun, and I can demonstrate this to you by doing the following. So we're going to place TRAPPIST right here. We're also going to maybe remove all of the particles and dust and fragments, accelerate time a little bit, and so let's see what happens. So sun has changed direction. Are the terrestrial planets still in orbit around it? It looks like it. And it seems like TRAPPIST was also able to capture Jupiter, making it its own planet. But as you can see, the terrestrial planets are orbiting just fine. Their orbits have changed just a little bit, but not enough to cause dramatic changes, or have dramatic effects. It's very interesting though how Jupiter was actually able to be captured by TRAPPIST. Let's see what Jupiter looks like from this distance. So it's become a very super hot Jupiter, essentially. It's actually a type of a planet that we've discovered. It's called super hot Jupiter. It's a gas giant that orbits around a star very, very closely. So maybe just maybe somewhere in the universe, one of the super hot Jupiters was actually born in the same way where I just created it by accident. It passed by a red dwarf too close to it and was captured just in the same manner. Earth is, oh, it's a little bit hot here. 31 degrees Celsius. Interesting. So yes, Earth has changed its orbit with time and will very likely change even more. The only reason it's so hot though is not because it's actually closer to the sun, but because there's actually another star warming her up from the other direction. So there's actually now a lot more seasons. A lot of interesting seasons. So like right now this is the winter because Earth is on the other side. And when it's between the two stars, you're going to have summer and mini summer, I guess. Or I guess there's going to be a lot more hotter here on this side because the Earth is warmed by two stars, even though the other one is a little bit farther away. But it's definitely affecting the temperature. And the last simulation I wanted to do is if I place TRAPPIST somewhere in the Kuiper's belt or even beyond it. So what if I place it somewhere really, really far away? Somewhere in the distance of about 60 astronomical units or so. So right here. Let's add all of the planets. And now let's just run the simulation for a little bit and see what actually happens to our sun and to the other planets as well. So we might actually have to remove some of the other objects so the simulation runs a little bit faster. And then focus on the sun and also focus on the planets like Earth. Now I'm actually going to create a barycenter because I want to see where the barycenter of these two stars is, and it's actually right here. It's far, far away, close to the orbit of Jupiter. So that means that the sun is actually going to be making quite a large circle here. As you can see, this is going to be the orbit of the sun, and that's the orbit of TRAPPIST. This is actually very, very interesting. Now this creates a really interesting situation because I would like to actually see if any of the other planets will be captured by TRAPPIST. So let's maybe just go here for a second and remove the TRAPPIST's own planets. I'm also going to remove some of the inner planets in our own system, like for example Mercury, because it moves a little bit too fast and slows down the game too much. But Venus, Earth and Mars will stay where they are. And we're going to now watch what happens to all of the planets as TRAPPIST slowly makes its way around the sun and the sun makes its way around TRAPPIST. So right now the sun is actually moving. You can't really tell, but well, actually you can't tell by looking here. It's moving at a speed of about 20 something meters per second. Very slow, but it's definitely moving. And where is it moving? Well, it's moving in the direction of this line that you see, because it's actually orbiting the TRAPPIST star. But because it's doing it so slow, there's a very, very high chance that none of the planets will actually be affected this time. So I'm going to accelerate this a little bit more just to show you that even as TRAPPIST makes its way around the solar system, it only affects the outer objects. So a lot of these Kuiper Belt objects, a lot of these dwarf planets, including of course possibly Pluto, will definitely be affected by it. Maybe even Neptune. Neptune too might be affected by this, although not as much as the Kuiper Belt objects. But the inner planets are not going to be affected by it. They're still in the same orbit as they were, and I can actually double check that by going to, for example, Earth and looking at the semi-major axes and also eccentricity. They haven't really changed that much. As a matter of fact, the semi-major axis of the actual orbital radius from the Sun is pretty much exactly the same. So you can kind of see that the Sun is following a path and the planets are just kind of orbiting around it. And because we don't really detect any motion from our Sun that you see right here, and because we don't really see any serious gravitational effects from a potential brown dwarf somewhere on the outskirts of our solar system, it's very likely that there is really no nemesis or no killer star on the outskirts, as so many of you ask me to talk about. I guess people like to have conspiracy theories, but you know what? This is all about science, and the science tells us that, well, we only detect some gravitational effects on the dwarf planets, and because of that we think maybe there is an object called Planet 9 somewhere far away from our Sun, but that object is definitely not as big as TRAPPIST. It would only be just a little bit smaller than Neptune. Well, anyway, so that's essentially what would happen to our solar system if you place TRAPPIST-1 and possibly its own planets around our solar system. As you can see, it does have quite a dramatic effect on our solar system, but it only affects certain types of planets depending on where it's located. So let's actually start by adding Jupiter to this system. Why? Well, because I want to actually show you the comparison between the size of the TRAPPIST-1 system and the system of the biggest gas giant in our own solar system. We're actually going to place it a little bit maybe farther away, just so that we can create a stable system here. And so there is Jupiter, there is TRAPPIST. And so now let's go in here and click on the action of adding moons to the planet. And look at that. Look at the size of Jupiter in comparison to TRAPPIST. It might be hard to tell, but if I were to actually add orbits here, you would see that in terms of size, basically TRAPPIST is even a little bit smaller than the Jupiter system. Now, it doesn't mean that it is smaller, because it's very likely that there's a lot of smaller objects that we haven't detected around TRAPPIST system. Like there might be smaller planets, smaller planetoids, and dwarf planets orbiting around it, far away from the location of even TRAPPIST-1H. But in terms of the actual size of the bigger moons of Jupiter, so there is TRAPPIST, with the farthest farthest planet being at a distance of about 9.4 million kilometers. And here is the system of Jupiter with its Galilean moons, and the farthest moon of Jupiter, Callisto, is at a distance of close to about 2 million kilometers. So in other words, the system of Jupiter is just a few times smaller in terms of radius in compared to TRAPPIST, but when it comes to actual size of the planet versus the star, this is Jupiter and this right here is TRAPPIST. So it's actually just a little bit smaller than TRAPPIST itself. So Jupiter system is a very good representation of what TRAPPIST looks like. This of course applies to other red dwarfs as well. Let's actually do this again for another really famous red dwarf, the closest neighbor to us, Proxima Centauri, with its excellent, beautiful, Earth-like exoplanet known as Proxima b. If I were to place Jupiter here again, and give it all of its moons one more time, you can actually see that the distance between Proxima b and Proxima Centauri is once again not that far off from a distance to the farthest moon of Jupiter. So here the distance is about 2 million kilometers, and here the distance between Proxima b and Proxima Centauri is only about 7.2 million kilometers. So maybe in terms of radius it's about just over 3 times larger. And how big is Proxima Centauri compared to Jupiter? Well, let's go there and check it out. So there is Jupiter, and here is Proxima Centauri, which is, once again, just a little bit bigger than Jupiter. So a lot of red dwarfs in our galaxy, and there's actually close to about 90% of all of the stars that are red dwarfs, will be very, very, very similar to Jupiter. And they will actually reflect Jupiter in many different ways, including the fact that many of the moons will be tidally locked, or I guess planets around those red dwarfs will be tidally locked. Many of them will also exhibit very similar other orbital parameters, and also very likely be affected by their parent star in the same way that the moons of Jupiter are affected by it. For example, one of the biggest effects that Jupiter has on its moons is the super high radiation from its huge magnetosphere. Its magnetic field covers a very large area, and the moons of Jupiter are highly affected by it. Now, this might actually happen around these red dwarfs as well. So there's quite a lot of different effects that might prevent planets that orbit red dwarfs from basically having inhabitable planets, which doesn't really give us a lot of hope, unfortunately. And of course, if we go back home to our own sun, if we take a look at our own solar system, we can kind of realize pretty quickly that in comparison to all of this, TRAPPIST system is actually very, very, very tiny. So I've done this before where I basically placed it somewhere right here, and you would notice that even if I add all of the planets to TRAPPIST, they're so tiny, so insignificant. And there's actually one that just accidentally left the system. But yeah, they're so tiny and so small in comparison to our whole solar system. Which once again means that our sun and our solar system is very, very unique. Not only is our sun very calm compared to other stars, specifically red dwarfs, our sun also seems to have very unusual parameters for its system. It seems to have terrestrial planets on the inside. It seems to have gas giants on the outside, and it does seem to have very hospitable conditions for water and for essentially life on Earth to develop. We haven't really found a system just like it, and we'll probably still keep looking for a very long time. So even if I look at these nearest 400 stars, the newly added simulation in Universe Sandbox Square, even if I look at all of these stars in our neighborhood, it's very unlikely that most of them will be as calm, as perfect for us to actually find a habitable planet around them. Stars like Barnard Star or Gliese 1214 or this one right here, Wolf 630A, will be red dwarfs. They'll be too active, and they'll very likely have planets that are tidally locked to their stars. And other stars like, for example, this one here with a very difficult name of 9 Alp 2 Lib, or even more famous stars like Altair, that's actually right here, are possibly a little bit too large and a little bit too hot to have a habitable planet anywhere within its vicinity. But we don't really know just yet because we haven't really found anything interesting about Altair. So a very new study published in June of 2017 talks about what each of these planets in TRAPPIST system may actually not only look like, but what they actually are composed of, and specifically explores the idea of them potentially being habitable and Earth-like. Now, prior to this, all of this was a speculation. We kind of knew their masses that were discovered based on the observations in comparison to the mass of the sun. And we kind of knew what they may or may not have, such as, for example, since they're all tidally locked, they all probably have very hot one side, very cold other side, and possibly like a twilight-like area with maybe liquid water on the border here. In Universe Sandbox, unfortunately, they don't really look like this, but you can check out one of my previous videos where I actually showed you what they may look like. But in reality, though, a lot of the newer studies started to reveal some really incredible things about these planets, and specifically that it seems that most of them maybe are Earth-like in terms of composition, except for the last one. And so today we're going to investigate this, and I'm going to kind of talk a little bit more about how the scientists actually figured this all out. And so let's start with the one planet that is probably not going to be very hospitable to human colonists because it's actually apparently 25% water. So this is actually the planet TRAPPIST-1F. We're going to zoom into it. And so the scientists, specifically here, we're talking about a researcher by the name of Dr. Quarles, a former researcher at Homer Dodge Department of Physics and Astronomy at the OU College of Arts and Sciences. A pretty long name. But anyway, so this person studied these for quite a while, and he basically just used various simulation to try to estimate what kind of planets might be actually created in this type of a system, and then also looked at the so-called eclipses of various, or not various, but all of these objects as they passed in front of the star. So this would be an example of an eclipse. So let me just actually remove some of these so you can see them better. So when a planet passes in front of the star, it eclipses it a little bit, and so the luminosity of the star decreases. And that way we can actually determine the size of a planet. So obviously if the planet is very large, it's going to cover a bigger part of the star, and if the planet is very small in terms of radius, it's going to cover a much smaller part. And so that's what the scientists in this particular study did. And it turns out that TRAPPIST-1F is slightly larger in terms of size compared to everything else. And even though its mass is approximately 70-ish, 67 or 68% mass of Earth, it's actually about the same size as Earth, which suggests that it is actually about 25% water. And so here we go. So it's about 25% water, meaning that the majority of this planet is probably either covered with very unusual gas-like water on this side because it's facing the star at all times, then probably has some kind of a liquid water here and very likely has ice deposits here, or for all we know, it might actually be completely different. It might be a very unusual type of a planet. But the important thing here is that because its size is very similar to the size of Earth, so here's Earth for a comparison. So there's Earth and there's TRAPPIST-1F. And because the mass of this planet is much lower than Earth, we can estimate that it's probably made up of more, or sorry, not more, but less dense materials, making its density much lower, probably something like 3.2 or close to 3 grams per centimeter cube, which is consistent with some of the moons of Jupiter, for example, and moons of Saturn that are actually made up of a lot of water. And so for all we know, this is actually going to be a very interesting world that is something we've never seen before. But the other worlds might actually be familiar to us. And specifically here, we're talking about all of the other objects in the system. So it turns out that all of the other 6 planets in TRAPPIST system are actually rocky. As a matter of fact, their density is very similar to density of planets like Venus, Mars, Mercury, and Earth. So if we go through them individually, you'll see that their composition is relatively similar to Earth in terms of amounts of silicates and iron. And we don't really know if there is any water. We don't really know if there's any atmosphere, of course. Chances are probably maybe not, but maybe there is some if they have magnetosphere. Of course, the only difference here is TRAPPIST-1F, which is 25% water, or possibly some other ices, some other things like methane and ethane, but it's probably just water. And interestingly, all of these were discovered basically using the same technique of so-called photometric observations, basically looking at planets as they pass in front of the star. Let's actually see if we can simulate this. As they pass in front of the star, there you go. There's a bit of a occultation, a bit of a decrease in luminosity. And depending on how much luminosity is decreased, we can actually estimate the size of the planet. And then we can use that, knowing the mass of the planet, to try to estimate the density, because density is always mass per volume. But at the same time, this also creates a really, really interesting opportunity for some of the other planets here, specifically planets like TRAPPIST-1D and TRAPPIST-1E. Now, both of these are in the relatively okayish region of the solar system, in the Goldilocks zone, or basically the habitable zone. So maybe, okay, maybe this one is a little bit too close, so it might be a little bit hotter, but 1E and also to some extent 1G are terrestrial, and the only thing we don't really know about them is if they have magnetosphere and if they have liquid water. So these two objects, and possibly this one here, are actually now very exciting for us to study, because we now are pretty certain that their composition is very Earth-like. And this also means that they might be very Earth-like objects, not too far away from us, only within about 40 light years away from our planet. And at the same time, these types of stars, even though they might be very active, will live for a very, very, very long time. As a matter of fact, red dwarfs can live up to several trillion years, which is like thousands of times longer than our own sun, meaning that these planets will actually have this kind of environment for billions and trillions years to come. So for all we know, there might not only be life here that already has developed, but we might be able to use these planets later on for our own existence, and we might be able to find someone to coexist here with as well. And so this new research definitely increases the chance for at least 3 or maybe at least 2 of these planets to be colonizable, habitable, and maybe even already have life on them. So by now we know that TRAPPIST-1 is a very interesting system. It's not too far away from us. It's got this very unusual red dwarf in the middle that's very ancient, older than our own sun. And it has 7 Earth-massed, or very similar to Earth-massed planets orbiting around it. But the problem is that they're too close. Most of them are probably bombarded by a tremendous amount of radiation from all of these flares that you see. And the other problem is that they're probably also very likely tidally locked to the star, meaning that the same face always points at the star and the other face is always away from the star. And in previous videos, I talked about how it's very likely that due to this tremendously powerful red dwarf, it's very, very possible that there is no atmosphere and possibly even no water left on these planets. But there is a new analysis coming out of the interwebs, and basically this new study shows that, well, it's still possible that most of these planets may have actually had a lot of water on them to begin with. So even after billions of years of being bombarded by this unusual star, some of them may have actually maintained some water. So let me just go back a little bit and try to talk about this in a little bit more detail. So let's start from scratch. First of all, there's 2 types of energy that might be bombarding this planet that is important for us. So for example, TRAPPIST-1e here is probably receiving low energy UV light and high energy UV light coming out of TRAPPIST-1. Just like Earth does, basically. So these 2 types of energies do 2 different things on the surface of this planet. The so-called low energy UV light bombards the planet, and we can kind of simulate this by literally bombarding the planet with these pulses that are going to be coming out of the star. So here's that low level UV light that's going to be coming here. And when it arrives to the planet, what it's going to do is it's going to take water molecules, and here it might be ice or it might be liquid water, and then separate it into hydrogen and oxygen. And it's going to do this for billions of years. So what happens when you separate water? It creates oxygen. And of course hydrogen, but oxygen is kind of important. So this already by itself creates a possibility for some of these planets to have oxygen on them, which is very, very interesting. On the other hand, there's also the high level UV light. So let's do this again. This time it's going to be the high level UV light. And this light takes those molecules, oxygen and hydrogen, and energizes them to the point where they start leaving TRAPPIST-1. So basically what happens is the atmosphere that might have been created from the low level UV light is now actually going to be turning that UV light into essentially escaping molecules. So Okay, that was too fast. Let's do it a little bit slower. So these molecules might now be actually escaping from this planet, and they're escaping because the UV light energized them to the point of their escape velocity, and they're basically going into the rest of the solar system. Now this is oxygen and hydrogen, again, more hydrogen than oxygen because hydrogen is much lighter, but this doesn't change the fact that if there was a lot of water to begin with, this process might still be ongoing, but it also might mean that there's still water on the surface, and there is still possibly even some oxygen circulating in the atmosphere. And the scientists studying these planets discovered that, well, it's very possible that in that period of time since the creation of the system, since the planet's existence, the 6 innermost planets, so the planets that are inside the solar system here, may have lost up to about 20 Earth oceans worth of water. In other words, if you look at Earth, if I add Earth here in the binary orbit with this planet, so we know that Earth has this much water in it, and TRAPPIST-1e would have lost about 20 times the amount of that. But that still doesn't change the fact that there could have been more water to begin with. And so according to this paper, it's possible that the outermost 4 planets, specifically E, F, G, and H, so this is one of them, may have lost anywhere from 20 to even maybe only 3 masses of Earth amount of water. So this times 3 to this times 20. Now, if there was not much water to begin with, then that still leaves us in the same situation as in previous videos, where we have no water, no atmosphere, nothing left because of the tremendous amount of radiation coming out of TRAPPIST-1 star, because it's a relatively active red dwarf. But if there was a lot of water to begin with, as a matter of fact, if it was mostly water, or if there was a very large chunk of water on the inside from the start, if it was a water planet to begin with, then these planets haven't actually dried up yet. They are drying up, but and that's, of course, even if they have magnetosphere, they're still drying up because the radiation is just way too powerful. It's like thousands times more powerful than it is on Earth. But even after billions of years, this water is still probably there if there was a lot of it present, and it's actively being deconstructed into oxygen and hydrogen. It's actively being released into the outer space, and so this solar system might be very unusual. It has a lot of oxygen, a lot of hydrogen in the interplanetary space. This might even be creating these unusual objects on the outskirts, like comets and asteroids that we haven't detected yet. But most importantly, on the planet here, this side of the planet might be creating a lot of oxygen that then sort of circulates around and might be surviving on the dark side of the planet. And so this might be a world that we can't even imagine. It might be actually a world full of oxygen. It might be a world full of water, liquid water. And if all of these planets were environmentally rich in water ice from start, basically if they were very rich in water ice when the system was created, in that case, then maybe all 7 of these planets have these unusual water environments, with the closest planet being basically full of boiling water, super hot water that we can try to generate here. So water that's ridiculously hot and is just creating these unusual clouds everywhere, which is actually how we could potentially detect if there's water here. If we detect a lot of clouds in the atmosphere, and the clouds of course have high albedo, so that's how we could measure it. If this planet has a lot of albedo, if albedo here is very high, we know this is a water world with potentially a lot of clouds. And with the outer planets being super rich in water ice and basically being covered entirely in it, and this water ice might still actually be creating oxygen in the atmosphere, thus giving these planets atmospheric pressure, obviously cold temperature, but also atmospheric pressure that would be enough for us to actually walk on. So all of these are speculations, but these are positive speculations, and time will tell if this is true. Now, we know that when Earth was created, it was relatively water poor. So a slightly different mechanism would have to create these planets. Most of the water on Earth came from collisions from other objects, like mostly comets and asteroids. And we still are not actually sure exactly where it came from, because some of the comets we've studied have different type of water on them, so we don't know if it was comets or asteroids. But for water to be on these planets, they would have to actually be created on the outskirts of TRAPPIST. So they have to be created somewhere, maybe right here. And then, with time, they would have to migrate closer and closer to TRAPPIST, bringing that water with them. So that's the only way that they could have so much water from the beginning. Otherwise, we're still stuck with those relatively dry and relatively empty TRAPPIST planets. Alright, so just to summarize, the new study suggests that even with the amount of radiation coming out of TRAPPIST-1, it's possible that the water here might not have all been destroyed. It might still be present on the surface and be actively destroyed, but still have enough to go for billions and billions of years. It doesn't change the fact that these planets are very dangerous to live on because of the radiation, but it changes the fact that these might actually be not dry worlds, but water worlds with atmosphere. But at the same time, this can only have happened if these planets are created on the outskirts of TRAPPIST-1 and then migrated toward TRAPPIST-1, forming the position where they are right now. Now, we currently think that this is maybe what happened, but there might have been a completely different creation story here, and we might actually not be certain how these planets were made. So within the next decade, we'll hopefully discover more about this star, and maybe even come up with technology to be able to visit it. Right now, it's just a speculation, and we'll have a telescope ready, known as James Webb Telescope, in the next few years to try to observe this in more detail. So why exactly are we talking about this? Well, one of the main reasons is because normally, if you have so many planets close together and a star in the middle and planets are relatively large, it's very, very difficult to actually create such a stable system. Let me show you an example. Let's just randomly create a system with a star in the middle and place a few random planets around it. Okay, some of them actually already fell apart. And just kind of run the simulation for a little bit just to see what happens. So you may notice that it's not really visible yet. Now let me actually just delete the fragments here, because this will cause the game to be too slow. We might actually need to place more planets on the outskirts, because they're actually warming up a little bit too fast. And so here I had to just change the system a little bit to make it run a little bit faster. And so here you go. As you can see, some of these orbits are already shifting around and are moving closer or farther apart. And at some point, the system might actually kind of fall apart. And when the scientists ran simulations for TRAPPIST-1, this is exactly what started happening. And they actually started thinking, well, how can the system stay so stable? So what they did was this. First of all, they took a look at it and thought, well, maybe it is actually in the process of transition and planets might actually collide soon, and maybe it is that one random chance of seeing the star system where things are just shifting around and moving around. But unfortunately, if you look at the timescales of normal solar systems and the chance of encountering such an event, it's almost impossible. It's actually so tremendously minuscule that the scientists started thinking, well, maybe there is something else going on. And what they started doing is they started counting how many orbits each of these planets makes around the star in a certain period of time. And what they realized was really remarkable. It's something that we've discovered a long time ago in many different other systems, like, for example, Gliese 876 and Kepler 223. And we might even have these actually here. And there's a Gliese system. And what we discovered was what's known as the planetary resonance. And basically here, specifically in this system, for every one orbit of the farther system, the closer farther planet, the closer planet makes 2 orbits, and the closest planet makes 1 orbit, and this one makes like a lot of orbits. And they all basically kind of connect in this very unusual pattern of resonance, which is basically a pattern of orbits. Now, we also have these around most satellites in our solar system. We have these around some of the planets as well. And what was remarkable about TRAPPIST was that this was the biggest resonance we've ever seen in astronomy. This is actually the longest resonance we've seen in terms of the actual number. So here, for one orbit of the farthest planet, or actually not for one, but for two orbits of the outermost planet, which is TRAPPIST-1H, the next planet makes 3 orbits, this planet makes 4 orbits, this one makes 6 orbits, then it's 9, 15, and the last one, the closest planet, makes 24. In other words, every 2 orbits of this one makes 24 orbits, or every 1 orbit of this one makes 12 orbits. Now, this kind of a resonance is what keeps these planets from colliding. They basically keep each other in check through gravitational interactions, which are very, very common in astronomy. And achieving such resonance, well, it is by chance, but it is kind of difficult. And what's really interesting about TRAPPIST-1 is that because the planets are so close together, because they're so massive, this is actually the only way for them to survive for such a tremendously long time. Now, that's not all I wanted to talk about. I actually wanted to show you a simulation that helps you visualize, or not visualize, but hear this resonance in a little bit more detail. And this is a simulation by Canadian scientists. You can learn more about them by going to the website that I posted in the description below. But basically, it kind of looks like this, and it's called TRAPPIST Sounds. They actually simulated it in many different ways, including a YouTube video. But we're actually going to play this resonance directly by using the little app they created on the website. So here, you can actually add the melodies from each of the planets by adding them individually. And the reason they added this kind of a simulation is because, well, they realized that scaling system orbits into tones actually makes a lot of sense for human mind, and this repetitive pattern is very easy to represent in terms of music. So every time a planet passes a certain point, it makes a different tone. And when 2 planets come close to each other, they make a drum beat. So if you can think of this in terms of music, you could actually create quite an interesting melody for each of the systems and each of the solar systems that we discover by using this type of technique. And this is actually very, very brilliant and super fun. So this is, I believe, was created by a person by the name of Matt Russo, and he created this musical representation where we can basically just play this. Okay, so I'm going to slow down tempo here because it is going to get pretty loud, but this is actually really cool and really brilliant when you think about it. So representing solar systems with this type of musical interaction can actually maybe help us navigate the stars in the future and help us understand where we are, and most importantly, give us an idea of how to better define solar systems. So this is a pretty cool simulation. There's another one for Saturn as well, and Saturn moons and their resonances. But we definitely have these everywhere in space, and creating music out of it definitely adds a little bit of a new note, pardon the pun, for this type of a field. Anyway, so that's all I wanted to talk about in this video. I wanted to show you the simulation, talk about the resonance of TRAPPIST-1, and give you an idea where you can learn more about it by basically visiting this website. So for several years now, we've actually been talking about the possibility of life evolving around red dwarfs. And when we found TRAPPIST-1 with its 7 terrestrial planets, this possibility actually kind of increased. And then it suddenly dropped when we realized that a lot of red dwarfs are too active. They have too many flares, and they basically strip their planets that orbit around them of any potential atmosphere and water. Although in some cases, maybe just maybe, there might be some water left, at least on the opposite side of the planet. Anyway, so we still don't really know if and how these planets look. We might be able to find out in 2018 when James Webb Telescope takes flight and is able to actually look at these planets. For now, we can only speculate and use theory of stellar formation to try to estimate what's going on here. But there's still quite a lot of actual theories that think that maybe, just maybe, life could evolve on one of these planets, and maybe even some, maybe even more than one, potentially some in the habitable zone right here. And because these planets are so close together, life could even spread from one planet to another via various asteroids due to collisions. But let's not rush ahead. So, if there is life on, let's just say, TRAPPIST-1e, how could it potentially evolve? Well, today we actually think that life on Earth may have originated around these things. These are so-called hydrothermal vents, also known as black smokers, or possibly inside caves. Now, if life did start around these unusual formations that are usually underwater, could it have also started right here on TRAPPIST-1e, assuming there is water somewhere on the opposite side of the planet? Well, if we assume that life did evolve around hydrothermal vents and life can sustain itself there, then it's possible that resistant organisms could actually colonize these habitats quite easily on other planets and possibly even develop some sort of a protection against these flares with time and then evolve onto other parts of the planet. So there is a slight possibility that this is actually a reality not only on other planets but also in our own solar system, on moons of Jupiter and Saturn, for example, because we have already discovered that they probably have these hydrothermal vents as well. We've also discovered various organisms living inside caves around the world, including some organisms that actually became blind over time. And so we know that life can totally evolve in caves as well, specifically really dark caves that might be protected from solar flares and harbor all kinds of creatures inside. But that's also a speculation, and I guess we wouldn't even know if life can actually live outside of those caves, or if it would be contained only inside of these very unique environments. But obviously there are caves on pretty much all of these planets, mostly because that's kind of how terrestrial worlds work. You kind of expect them to have caves, and if there are caves on, for example, TRAPPIST-1g, then maybe, just maybe, we can discover a creature that looks something like this, or possibly something completely different. So there's definitely a possibility that life could have evolved on caves in a TRAPPIST-1 system. Other creatures might actually survive by burrowing themselves inside mud or earth or something else. Like, for example, this is a very unusual creature known as a bobbit worm. It can reach several meters long and it can be absolutely terrifying and can actually kill fish really fast. This is from Smithsonian Channel. It posted this video of a bobbit worm that was discovered by one of the divers, and these types of creatures can definitely survive by burrowing inside underwater, and this could definitely protect them from solar flares as well. And then there are these creatures called tardigrades, also known as water bears, that are known to survive hostile environments, including, of course, space. And these creatures can actually develop a very unusual shell that prevents desiccation and prevents damage. That will usually protect them for some time, and then they can kind of get rid of the shell and continue their life when the environment becomes better for life, more suitable for life. So it's possible that some life on TRAPPIST-1 and other around other red dwarfs has developed these types of protection devices as well. And then there are creatures that might have shells to protect themselves from all kinds of dangers, including solar flares, and maybe, just maybe, these shells might be enough to protect them from solar flares if they actually have some sort of metal or even other materials that would protect them from radiation. And when you think about it, even primates have a sort of a protection. Our hair is actually a type of a protection from the sun because it's essentially made out of dead cells, and mammalian hair is very good at protecting us from all kinds of dangers. So it's possible that some creatures on other planets may have developed tremendously large hair to protect themselves from solar flares. At least that's one of the ways we can protect ourselves as well. And on top of that, on Earth, we have things like plants that can actually survive quite a lot. Even during forest fire, most trees actually survive because their roots are completely untouched, so the entire forest, even after it burns down, gets repopulated pretty quickly within only a few years. So on a planet in the TRAPPIST system that might experience a lot of solar flares or might even experience some sort of a fire, the creatures that have to deal with this type of problem might actually lose the parts that are above ground, but everything inside, underneath, will survive just fine and will actually start a new cycle as soon as the flare is finished. So there's quite a lot of possibilities for the existence of life in TRAPPIST system and also around other red dwarfs. And for all we know, maybe just maybe all of these situations are actually happening there right now. We won't really know for quite a while, and we won't be able to even see if there is anything life-related happening for at least another decade, because we don't have enough equipment to do it. Although when it comes down to it, maybe just maybe some of these planets, at least one of them, 1 out of 7, has just the necessary conditions to have at least some sort of extreme life that might live there. And if you actually play around with the numbers in Universe Sandbox, you might discover that you can actually create the conditions where the chance for life is over 60%, which is by itself quite impressive. So the chance for having some sort of life in TRAPPIST-1 right now is pretty high. Whether it is there or not, maybe one day we'll discover, maybe not. So the TRAPPIST-1 system is actually a relatively recent discovery, but even today, scientists are really busy trying to find out as much about the system as we can for 2 reasons. One is that it's actually kind of close to us. It's only about 40 light years away, and that's really close when it comes to stars. And second of all, the reason that we're most excited about it is that it actually has 7 what seems to be terrestrial planets. Now, we don't really know if they're habitable or not, but we got a little bit closer to understanding what's happening here. Specifically, we actually did the following. There were 2 separate studies and 2 separate analyses, which basically did 2 things. One of them actually looked at the passage of planets in front of the star and looked at the minute changes in the spectrum of the starlight right around the edge of the planet, or specifically each of the planets. And this was meant to try to study if these planets had atmosphere on them. Now, because it's actually a relatively difficult task and requires really powerful telescopes, the first attempt wasn't really successful at finding the actual atmosphere, but it did discover that there is no hydrogen around most of these planets. This suggests that these are obviously not gas giants or gas dwarfs in this sense, but also that these are not new planets that would have hydrogen. So there might be some other stuff here, but definitely not hydrogen. And if there is an atmosphere around these planets, we know that it would probably be made up of carbon dioxide, oxygen, and potentially methane. And so we're now going to be looking at those particular spectra to try to see if there's anything else around them. Now, this is not particularly an exciting finding, but you know, sometimes not finding something or finding that something is not there is just as important as finding something that is there. And then the second study actually did something a little bit more complex. It was based on observation of orbital perturbations of these planets as they orbit around the star, but also as they pass by close to each other. So these are not perfect circles, and these are not even perfectly fixed elliptical orbits. Each of these planets influences each other as they orbit around TRAPPIST-1. Now, we don't really see it with our own eyes, because it's very minute, it's very tiny. But a computer can totally see it. As a matter of fact, what the scientists did is they created a simulation, which they run basically thousands and thousands of times to try to find out what was the most accurate representation of the orbital path here compared to what we see. In other words, they basically ran a simulation and then they looked at the results of what we really see and tried to estimate which of these simulations was most accurate. And turns out, using the simulations, they were able to discover really important factors about TRAPPIST-1 planets. They discovered their mass, and to some extent we already knew their size, so they basically discovered both mass and size, and thus density. Now currently in this particular simulation, this is a bit outdated, so the density here is not actually that accurate. As a matter of fact, the size is not accurate either. I'm gonna show you the most accurate representation we have as of today, and here it is. And this right here is based on the analysis by NASA, and basically it kind of gives you an idea of how these 7 planets compare to our own planets. Now, just to summarize, so the density is right here, the surface gravity is right here, and mass and radius is right here. What is interesting here is that none of these planets seem to have higher surface gravity than Earth. As a matter of fact, Earth so far is the winner in terms of gravity. But this object right here, TRAPPIST-1e, seems to have higher density. And that's despite the fact that it has lower mass and lower radius, which would suggest that maybe it has some sort of a highly metallic core on the inside, which would also potentially suggest, if it actually is spinning a little bit faster than Venus, and as long as it actually has a spin of at least 6 days, which is its orbital period, and we assume that it is actually most likely tidally locked to its star, there's a high possibility that this planet right here might have relatively powerful magnetic field, which is really important for maintaining liquid water and of course a magnetosphere. Now, other planets are not as exciting. As a matter of fact, here the density is even lower than Venus, and this particular object that we were super excited about might actually be the least exciting of them, because the density here is much lower than any other planet in TRAPPIST-1, and is actually even lower than the density of Mars, which is already not a very dense planet to begin with. Also, the gravity here is about half the gravity of Earth, and the other 3 objects, we're not really sure what's going on there yet, but we think that there might be actually some sort of a large terrestrial core and probably a lot of ice on the surface. Now let's actually just kind of summarize what we know about each of these. And let's start with the ones on the outskirts of the star system first. So TRAPPIST-1H, TRAPPIST-1G, and most likely TRAPPIST-1F are probably either frozen worlds, or if they have thicker atmosphere, they might be, let's actually simulate this right here, very interesting water worlds, potentially with some continents, but very likely just big water worlds with nothing on them, with most of the density being lower due to the fact that there's just so much water on the surface of these planets. All 3 of them seem to have relatively low density, which suggests very likely non-terrestrial materials such as ices. TRAPPIST-1e seems to be the most exciting discovery we have so far, because it does seem to have very high density, thus potentially really metallic core and potentially also magnetic field. And if there's magnetic field, maybe, just maybe, this is actually a very interesting habitable planet with quite a lot of liquid water and maybe even some kind of a really interesting atmosphere. So here, even with just a little bit of atmospheric pressure, you basically get temperatures that are comparable to Earth, and which is something that actually might give us a lot of hope for this to be an actual future home for humanity. So as you can see here, it's going to stabilize around about 20 degrees Celsius. So that is probably the most exciting discovery. But then there is some discoveries that were not as exciting. This is specifically TRAPPIST-1d, which seems to not be as terrestrial as we hoped. So this might actually be more or less icy body, or some sort of a body that's just covered with a lot of atmosphere, where it's probably not very dense due to a very large ice cover or some kind of a water layer, which makes it a lot less dense than other objects in the star system. So that's TRAPPIST-1d, unfortunately so far a disappointment. And then we have the first 2 objects, 1b and 1c, both of which appear to be terrestrial and relatively high in density. And TRAPPIST-1c, as a matter of fact, seems to be the second most dense planet in this particular star system. with very Earth-like gravity and potentially some atmosphere and potentially some water. Because it's so much closer to the parent star than other planets, it's probably also very, very hot here. So this might be actually a world similar to Venus, which we can try to recreate here by adding just a little bit of atmosphere and maybe some water, but then it will probably very likely evaporate really, really quickly. So this is essentially what we've discovered so far as of February 2018, and I'm sure as the time goes by and as we do more and more of these studies, we'll probably discover more and more interesting details about TRAPPIST-1 system. Now, if you enjoyed this video, don't forget to subscribe, don't forget to share this video with someone who enjoys watching space videos, and come back tomorrow to learn something else. And here we can actually see how TRAPPIST-1c is going to start losing most of its water as it gets hotter and hotter and hotter, because even a little bit of atmosphere here will probably create a greenhouse effect that would be extremely high. Now, for all we know, maybe just maybe these planets are actually habitable and do have a lot of water, but for now all of this is a bit of a guesswork based on what we discover using various telescopes. So a very, very recent study published in May of 2018 and actually still not completely finished by the scientists. This is by Gabriela Suissa and David Kipping. Basically talks about the planet here known as TRAPPIST-1e. Their study is based on a statistical analysis, which is by itself based on several other studies where we actually were able to estimate and establish the radii and the masses of the planets simply looking at the interaction they have with the parent star and with each other. So first of all, let's talk about the sizes of the planets. We can establish the sizes of the planets by essentially just looking at the star itself. Let's actually zoom into it and seeing how much the actual luminosity of the star changes when one of the planets passes in front of it. This is a pretty easy way of measuring how big the planet is. But when it comes to masses, it's a little bit more difficult. I've actually previously mentioned how they did this, but they looked at the interaction of the planets with each other. They were able to actually see at how the orbital parameters of each planet changed as they essentially orbited around TRAPPIST-1, and the various variations in the orbits can be actually used to establish the mass of each of the planets. And this is actually relatively accurate. So there's only about 5% error in this prediction. So this way we were able to establish the size and the mass of each of 7 planets here. And this is actually a pretty cool way of figuring out what each of the planets is and how big it is and how massive it is. But using this, of course, we can then figure out the density of the planets, and this is where things get interesting. Using the density for each of the planets, we're able to kind of estimate of what they might actually contain on the inside. And because we were able to establish the density and potentially predict the composition of the planets, we started looking at various planetary models and try to predict what's actually inside of each planet and what it can possibly have on the surface as well. And so this new study known as TRAPPIST-1e has a large iron core, kind of gives you the actual conclusion here. Of all 7 planets, these scientists relatively accurately were able to predict that the TRAPPIST-1e planet might potentially be one of the most Earth-like planets we've discovered so far, because statistically speaking, at a minimum, its core would actually contain at least 50% or possibly even 55% of iron. Very, very similar to Earth. Earth is actually at a value of about 50%. At a maximum, this would be about 78%. So this particular planet has a very, very, very large iron core that actually makes it extremely Earth-like. Now, because this planet is actually a little bit farther away from the sort of outer edge of the habitable zone, it might still be a little bit on the cold side, depending on the atmosphere that's present here. But nevertheless,
This iron core actually gives TRAPPIST-1e chance for not just thick atmosphere, but potentially also liquid water, because if it actually does spin fast enough and if it actually has this massive iron core on the inside that's also possibly molten and circulates around the planet, this would generate big enough magnetic field to protect TRAPPIST-1e from most of the solar flares that might be coming from TRAPPIST-1. In other words, this planet might actually be sheltered from various types of radiation that red dwarfs usually create. And most importantly, this would actually create conditions necessary for, well, really life. If there's liquid water, if there is atmosphere, if there's magnetic field, and if the planet is very Earth-like in its appearance, we can kind of expect this planet to basically have relatively Earth-like conditions on the surface. Now, obviously, it would not be as bright as Earth. It would definitely not resemble Earth in many other ways, and it might actually just have a bunch of ice on the surface here, like you can see here as well. But despite all of this, this beautiful planet, even if it is a nice planet, might have conditions that would actually be kind of life-friendly. So, despite the lack of brightness, it might still provide enough light for simple life forms. And the ices here might actually create various conditions that could shelter life underneath the ice as well. So there's a lot of potential and a lot of possibility for this planet to be very Earth-like. And if the atmosphere is actually thicker than this, so if this atmospheric layer here is a little bit different, and we can actually just change how the atmosphere looks by, I guess, modifying colors. For one, you can totally just go and change what it looks like in terms of the actual colors. So let's make it a little bit more green, give it some green colors here, and also change the atmosphere, making it slightly more blue, I guess, so it looks a little bit Earth-like, although that's actually clouds, so it's not atmosphere. But anyway, so we can kind of make it look slightly different and more Earth-like. And here, let's just close all of this, give it some more color, accelerate this, and see what it looks like. So for all we know, this actually might be one of the most Earth-like planets we've discovered. There is actually at least one more planet that has such a massive iron core that we know for a fact. And that planet is actually one of the Kepler planets. Specifically, it's Kepler 36b. And if you go to Kepler 36b, you'll discover that it possibly is also very, very similar to this as well. So let's actually go to Kepler 36 and jump to planet B. So interestingly, we still need a lot more studies to basically try to figure out what exactly is happening in TRAPPIST-1. Because it's a red dwarf, it obviously has very different conditions to Earth. It has very different conditions to our own solar system to begin with. But TRAPPIST-1 is not a very active red dwarf. And this actually gives us hope for it to be more Earth-like. So this is Kepler 36b. As you can see, temperatures here are a little bit hotter. And because of this, this is definitely not the Earth we're looking for. As you can see, there's a lot of lava on the surface, and we'll actually talk about this planet in one of the future videos because it is kind of cool in its own right. So when you look at our planet Earth, it seems very familiar, and it seems like every planet out there somewhere in the galaxy is going to be similar to it, or at least we hope so. Turns out though, as we study our planet and exoplanets a little bit more, Earth, the way it's formed and the way it is and the way it's structured and what's on the surface and inside of it is actually extremely rare. It's super rare to find a planet like Earth. The most common planet in our galaxy, as of the current understanding of exoplanets, is actually what's known as an eyeball planet. And I'm going to show you right now what the actual planet looks like. And I'm going to take you to a system where we think there's like tons of these eyeball planets. And it's actually a system we've talked about previously. Now this is the system I'm talking about, and if you haven't guessed yet, this is TRAPPIST-1. The system discovered just over a year ago when I'm making this video, that basically has 7 terrestrial planets, or terrestrial in quotation marks. Let me actually show you the structure of such planet first, by showing you the structure of these planets from the outside first. And this is kind of what these planets look like. Now, it may not resemble an eyeball just yet, and it might not actually make sense why it's called an eyeball planet, but if you were to look at it from different angles, you would realize that it actually has very different structures on the surface. As a matter of fact, it has extremely hot surface right here at all times, an extremely cold surface here, once again, at all times. And it has relatively temperate area right here on what's known as the twilight area. Now, this particular eyeball planet is known as a hot eyeball planet because it basically has desert or desert-like conditions on the warmer side and pretty much really cold, icy conditions on the other side. There's another type that I'm going to show you right now, and the best example here is TRAPPIST-1F. This is called a cold eyeball planet, and you can probably tell why. It basically has ice shelves here, and also obviously on the dark side, and essentially liquid water facing the star itself. And as you can see, simply from the actual visual representation, these planets are very unique, very unusual. We don't have anything similar in our own solar system, but they are extremely common simply based on one simple fact. These planets are the most common planets around what are known as the red dwarfs, which is the star that you'll see in a few seconds. That's a red dwarf. These are the most common types of stars in our galaxy. Something like 90% of all of the stars in our galaxy are red dwarfs, and the vast majority of them have planets, and most of these planets are usually similar to this. They're terrestrial in nature, but eyeball looking in appearance. Now, if you were to actually go a little bit closer, you'd realize that this side is always hot, this side is always cold, and this is the only side where you could potentially kind of have livable conditions because it's moderate, and this is where you would most likely find any kind of signs of liquid water. Although for cold eyeball planets, you might also find liquid water on the sun side because here the temperatures are just really cold in general. If you were to try to dissect the actual structure of these planets, this is kind of what it looks like. So first of all, why are they like this? Well, it's because all of these planets are tidally locked to their star. In other words, as they are rotating, only one side is facing the star and the other side is always dark. It's kind of like our moon, I guess. When you look at our moon, you always see the same face, or pretty much any moon of Saturn or Jupiter. Most of the moons of Saturn and Jupiter are tidally locked as well. Light comes from the star here. This is, let's say, TRAPPIST-1. And as the light comes in, it obviously heats up this part of the planet. So for most of these planets, they're going to be extremely hot. This is going to be desert-like conditions, extreme temperatures. And the other side, since it's always dark, is going to be pretty much ice. Now, assuming that there is any kind of atmosphere on this planet, it would actually create a relatively active, essentially, circulation here that would circulate the planet and most likely warm up this part as well. So it's not going to be super cold, but it's still going to be relatively cold. And it will actually create lots of clouds in this area, so the darker side of the planet. And there's going to be most likely either very few or very unusual clouds on the hot side of the planet. All of these planets will most likely also have quite a large ice shelf, and there's going to be a very unusual area right here on the what's known as a twilight zone or twilight area, where there's going to be quite a lot of liquid water as a kind of a band around the planet. And if it's a cold eyeball planet, it's also going to have more water pretty much everywhere here. Although the other side of the planet is going to be much colder and more inhospitable to life and habitation. Now, TRAPPIST-1F is actually a really exciting planet for us to learn more about because it might potentially have quite a lot of liquid water on the surface, simply based on the density studies we've done so far, and simply based on the fact that if it has one side always facing the sun, it's going to be warm enough to create liquid water, assuming that there is some kind of atmosphere here. It doesn't mean that it's going to be habitable to humans because it's most likely going to be a water world with a lot of ice. unless of course you're okay living in Antarctica-like conditions. And it's also going to be really dark here, but it might have potential conditions for life. On the other hand, all of the other TRAPPIST planets, especially the ones that are closer to the star, are most likely going to be similar to this, which is the hot eyeball planet. And so here you would most likely expect a very large desert-like area facing the star, with relatively temperate conditions on the twilight area, with water starting somewhere over here. Now, the reason why these stars are actually kind of important to study, and hopefully one day we'll even make it here, and the reason why these planets are so important to us as well is because, first of all, these are the most common types of planets, thus making the chance for finding life on these very, very high. On the other hand, these types of planets are also the ones that are going to stay with us the longest. Red dwarfs are the longest living stars. Their lifespan is over 1 trillion years, which is like hundreds of times more than a sun-like star. And so these planets in the future, if the humans are still around, might actually become our new home. So we need to learn more about them, and we need to find out if we can actually create habitable conditions on these planets, because it's important for our own survival as a species. Now, for now, that's all I wanted to talk about in this video. So now you know a little bit more about these so-called eyeball planets. And in one of the future videos, we might even try to make an estimate of how many such planets there actually is in our own galaxy. And the number is going to be completely outrageously large. So there's definitely going to be at least one of these planets that we're going to find that's going to be just perfect for humans. Hopefully in the next few years we'll discover more and more of these planets similar to TRAPPIST-1, and hopefully we'll even discover something else unusual about them. But for now, that's all you need to know. It's a type of a planet that's not available in the solar system, but is actually extremely common in our galaxy, making, once again, Earth an extremely weird, yet unusual, yet wonderful place to live on. So chances of us finding Earth-like planet is actually relatively low, but chances of us to find an eyeball planet that's relatively similar in at least temperature to Earth is pretty high. So in the last few months, specifically in the last, I guess 5 or 6 months since I made the last video, there have actually been quite a lot of studies. As a matter of fact, here are just some of the recent ones from the last few months. But the bigger studies were basically related to the actual nature of the exoplanets and essentially what's on the inside, what do they contain, and how do they possibly look, and most importantly, do they have any water or livable conditions on the surface. Now, by now you should probably be aware that TRAPPIST-1 basically has 7 confirmed terrestrial planets, or Earth-like in a sense, in terms of at least mass, but it's not necessarily true of their actual composition. And so the recent discoveries made the actual error of predicting the mass and the density of these planets much smaller than it used to be. We went down from about 10% certainty to basically about 90% certainty of what is probably happening in this particular system. And right here you're actually looking at TRAPPIST-1e, which is right now the most sort of hope-giving and the most inspiring planet that we've discovered, exoplanet that is, because it does seem to be very Earth-like. Anyway, let's take a look at some of the recent discoveries, and this is mostly based on a paper from Simon Grimm, who is kind of the principal investigator for these studies. And also this paper right here, Interior Characterization in Multiplanetary Systems, TRAPPIST-1. This is by Lilith Dawn and also Simon Grimm as well. So what did they actually discover, and what do we know about TRAPPIST-1 now after about 2 years of basically studying the system full time? Well, first of all, let me actually just explain to you how they even discovered all of this stuff. So originally, the way we discovered the planet is by seeing them sort of pass in front of the star, and so that way we were able to see the actual size of the star, of the planets. Because we kind of knew the size of the TRAPPIST based on analysis of other stars, we could then estimate or predict the size of planets because of the amount of luminosity that the star lost when the planet that you see right here passed in front of it. So this is kind of how we found the size, but we didn't really know the mass. And Simon Grimm's analysis involved the interaction of these planets between each other. Now, here's the cool thing about TRAPPIST-1. All of the planets here have what's known as a resonance. basically they're kind of connected in the way they orbit around each other. I think the easiest example of resonance can be actually seen right here around Jupiter. If you look at orbit of Io and compare it to orbit of Europa and then Ganymede, you'll realize that there's actually a direct relationship between them. For every 4 orbits of Io that you see right here, Europa gets 2 and Ganymede gets 1. So it's basically 4-to-1 resonance. In TRAPPIST system, it's a little bit more complex than that, but there is a resonance, meaning that you can technically predict where a planet would be. Even without looking at it directly, you should be able to kind of predict where it is based on the resonance. And the resonance there is relatively complex, but it is there. And so what Simon Grimm's team did was basically compare the visual observation with the predicted resonance-based orbits. And what they discovered was that sometimes the planets weren't really where they were supposed to be because they were interacting with each other. And that way, using a very, very complex mathematics, they were able to actually calculate the mass for most of them relatively accurately. And so because these planets always sort of tug on each other, the gravity of every planet influences the other planets, the team was able to use what's known as an n-body simulation. Basically, this is an example of n-body simulation where all of these planets kind of influence each other gravitationally. They were able to predict, using multiple simulations, of what composition and, in some sense, what density and mass was the most appropriate for the system. And in the end, they actually achieved something like 5 to 12% error, which was a dramatic increase from a 90% error that we had before. And the results were actually quite interesting. So first of all, the density of all of these objects is anywhere between 60% of density of Earth to just a little bit over the density of Earth, so just like 1.01. So that means that our old parameters here are actually incorrect. The density that we used to have for a lot of these objects is kind of wrong. The analysis also showed that basically TRAPPIST-1c and TRAPPIST-1e, these two objects, are the most terrestrial of them all. They're basically the most rocky and the densest of them all. Here the density is actually wrong as well, so it should be closer to about 5. So we're going to change that. And then interestingly, we also found that at least 4 of these objects probably have quite a lot of volatiles. These are usually things like water. So in other words, there could be tremendously large amounts of water stored here, something like 200 times more than on Earth. So this planet, TRAPPIST-1f, this one right here, TRAPPIST-1g, also the closer ones, specifically TRAPPIST-1d and TRAPPIST-1b, may actually contain a tremendous amount of water. And for D, G, and F, what this implies is that they probably look exactly like this. They're basically these large frozen worlds, similar to Europa, similar to Ganymede. At least that's the assumption right now, with about 5% of mass as volatiles, basically as ices. They kind of may resemble Ganymede. On the other hand, because TRAPPIST-1b is really close to its star, it probably has something different going on here. And the assumption here is that it most likely has a tremendous runaway greenhouse effect, similar to Venus. In other words, if we were to take a look at this and compare it to the planet on our own, in our own solar system, it would maybe resemble Venus, except that much, much hotter. So, okay, this is maybe a little bit too hot. Let's make it a little bit less hot. It would have a very, very thick atmosphere filled with water vapor. And there will be a lot of volatiles here as well. But because it's so close to the parent star, it would just basically be all as very, very thick atmospheric layer above it. And because there's a lot of greenhouse effect here, it would obviously be just as hot as Venus, possibly even hotter. So this is kind of like a Venus representative of TRAPPIST-1. While on the other hand, planets D, F, and G that I previously mentioned may not have any complex atmosphere at all. As a matter of fact, the scientists studying these planets don't expect there to be any complex thick atmosphere. Or if it is thick, it's going to be very simple, simply containing things like nitrogen, not carbon dioxide, not CO2. This also implies that the closest sort of equivalent in terms of atmosphere would be an object like Pluto, that I'm going to briefly place right next to this object here, because we know that Pluto has a very, very thin nitrogen atmosphere. These objects may have something similar as well, but not a complex atmosphere like we have on Earth or even the ones on Venus. Although nevertheless, it doesn't change the fact that B, D, F, and G planets actually have a tremendous amount of water, or at least some kind of volatile similar to water. So in that sense, these are technically water worlds, even though they might not have liquid water. They might have just ice shelves like TRAPPIST-1d here, or a lot of water vapor like TRAPPIST-1b. So water worlds, but not really liquid water. And then we come to the biggest surprise, or I guess it wasn't really a surprise because we expected that, TRAPPIST-1e, which, as you can kind of see here, is actually sort of in a habitable zone. It does receive a little bit more heat than our planet Earth does at this distance, but here what we do expect is an object that might actually contain a lot of liquid water, because we do expect a lot of water here. But at the same time, it's also a little bit more dense than Earth, and may actually resemble something similar to a super Mercury than an actual Earth. So it's not an Earth-like planet as much as it is a very unusual liquid Mercury. The actual mass of this planet, which I think is a little bit easier to see right here, is just a little bit less than the mass of Earth, 77%. And its radius is also smaller, but its density is a little bit higher. That actually implies that it's probable that this object received a very large collision early in its development that basically stripped the old TRAPPIST-1e off the actual mantle that kind of flew away and possibly collided with something else. And what was left was a very dense iron core, iron and magnesium specifically. And this is kind of what one of the explanation is, because otherwise it's very hard to explain why this object is so much more dense and has so much more iron and other metals inside than the other planets in the system. So this, in a sense, is a representative of Mercury-like planets, but at the same time it does seem to have what could potentially be atmosphere and also liquid water. So in some sense, this right here is actually the most Earth-like object we've discovered so far, at least according to the more recent analysis. Now, obviously, this doesn't change the fact that we could be still wrong about these objects, because there are other scenarios where all of this mathematics still works. Like, for example, maybe, just maybe, these planets are actually a lot less massive than we think, and maybe, just maybe, the actual density is wrong for all of them, and they all have like no water but very dense iron cores. But only the future studies will actually help us understand these planets a little bit more and help us understand if it's actually worth coming here and studying these planets in more detail. Now, I think I'm going to finish this video by going to this unusual, I guess it's an ice volcano or something, on the surface of TRAPPIST-1e in Space Engine. And we're going to take a look at what it all sort of looks like on the surface. But at the same time, we're going to wait for more papers to come out that might explain things that are going on in this particular star system a little bit better. As of now, though, this is one of the best mass and density analysis papers that I've read, and it's definitely something that will help the scientists in the future to study other star systems as well. Anyway, thank you so much for watching, and if you've enjoyed this video, maybe subscribe and share this video with someone who loves learning through video games and wants to know more about space sciences as well. Come back tomorrow to learn something else, and maybe even consider supporting this channel on Patreon, because it does help me a lot. And if you know any other cool papers about TRAPPIST-1 system or other unusual systems that you've discovered and want me to talk about, do post it in the comments below, or maybe even email me the actual paper so I can take a look at it. And here's with that volcano, basically the remnants of the old ancient volcano on the surface of TRAPPIST-1. It's all covered in ice now, but one day maybe it will actually explode again. And this is kind of what it looks like to stand on the surface or on the edge of this volcano in Space Engine on TRAPPIST-1e. The wonders of TRAPPIST-1 system. Hello wonderful person, this is Anton and welcome to TRAPPIST-1E. This is actually a continuation of our previous exploration of TRAPPIST-1 system, and this is actually related to a really interesting article that I accidentally found while looking for more interesting papers to read about this fascinating system. Now, we've known about this system for a long time, but the 7 planets that we know of today have only been discovered less than 2 years ago, and it's already sort of created so much buzz around the system itself that I don't even know where to start, right? We have planets that might be terrestrial, that we might have planets with tons of water on them, and most importantly, we might even have planets that have relatively habitable or livable conditions. But today we're talking about another interesting paper I've discovered that speculates about existence of yet another planet in the system, giving TRAPPIST-1 not 7, but maybe 8 terrestrial planets. So let me actually just show you this paper first. And this is by David Kipping, who actually did produce some interesting papers about the system already. And here he basically uses the analysis that technically not all scientists prescribe to, not all of the astronomers believe in this particular analysis, but it does seem to work. It's actually, I made a video about this previously. It's based on what's known as the Titius-Bode law. Basically, according to this law, and you can totally try this yourself, you could predict the location of the planets in our solar system relatively accurately if you apply his formula. As a matter of fact, it kind of works for a lot of the planets in our solar system until you reach sort of further depths, and then it doesn't really work as well anymore. And there's actually the rule versus actual distance right here. But there are several versions of this law, and some of them have actually been modified to work even better. And in this case, if you apply this law to TRAPPIST-1 system, it seems to work tremendously well. As a matter of fact, you can totally predict the location of the 7 planets using the modified version of Titius' law. You can read a little bit more about how Kipling did this in his paper, but the idea here is that you can predict all of these planets and the next planet using the law, along with the fact that a lot of these planets are actually in resonance. They have a kind of a rule between them where the resonance is very specific. But we're not going to go into the detail and the math behind this, but what we are going to do is talk about the conclusion and the discovery. And so what exactly does this paper sort of discover? And what it finds is that there is maybe, just maybe, a planet located at a slightly farther away distance with a period of either 28.7 days or 25.3 days. And the actual prediction here, assuming the planet exists, is very, very sound. It's very logical. So this is where the planet would be located if it was about 25.3 days in orbit. And the more accurate prediction would be actually a little bit farther away, right around here. So TRAPPIST-1I, if it actually exists, would be somewhere right here on the outskirts of the system. But because we actually haven't seen it traverse the star visually, we don't know if it exists. But here's the kicker, and here's basically where it becomes interesting. Assuming that this planet does exist and basically just kind of orbits not on the same plane as the other planets, but maybe just a little bit more inclined this way, so that this is why we didn't really see it. And it's kind of there and it does influence other planets gravitationally, this kind of actually throws our analysis of other planets well, into the garbage essentially, because we made a lot of assumptions about other planets based on the idea that there were only 7 planets in the system. If there's an 8th planet influencing these objects gravitationally, our analysis of the mass and the density of these objects is actually probably incorrect. So finding this planet, if it exists, is kind of important before we decide to go and travel to the system. Now, there's actually almost no way for us to currently discover it, because if we can't see it visually, we will very unlikely to discover it gravitationally, because it just doesn't really produce that much gravitational pull on the objects here. But it's still possible, assuming that we look at the system for a very, very long time and have very, very, very precise measurements. For now though, this is actually just a speculation. So in other words, this object TRAPPIST-1I, just like the other planets predicted by Titius' Bode law, might not even exist. but if it does exist, it definitely changes everything in the system. So this was a pretty interesting assumption and analysis to read, and it was actually very interesting to find out that Titius Bode law, as you can see from the graph here, seems to predict the position of the other planets, other 7 planets, exceptionally well. And so this is kind of where it got really crazy, and I wanted to talk about this in this video. So the 8th planet, the 8th prediction, would be maybe somewhere right there. And as you can see, even the author of the paper basically says that it's hypothetical, but if it exists, it's probably somewhere there. And so that's kind of all I wanted to talk about in this video. I wanted to explore the TRAPPIST-1 system yet again and talk about the potential 8th planet, which would still actually not make this system the record holder, because we do have other systems where there are 8 planets, and I'll talk more about them in the future videos. You may already be aware of which system I'm talking about, but I don't want to spoil it just yet, so if you do enjoy these videos, subscribe, click the bell button to be notified about videos upcoming in the future, and maybe even consider supporting this channel on Patreon, because, you know, it does help a lot. Anyway, so let's escape TRAPPIST-1e and go for a little trip across galaxy and see if we can discover something else really cool out there. Hello wonderful person, this is Anton, and in this video we're going to be returning back to TRAPPIST-1. The system discovered a few years ago that seems to have 7 terrestrial or very Earth-like planets that basically surprise the world. In this video specifically, we're going to be talking about a new study that talks about this planet, TRAPPIST-1g. So let's discover what's going on here, and welcome to What the Math. So if you were to take a look at the TRAPPIST-1 system in simulations like, for example, Universe Sandbox, you would actually even see where the habitable zone is and which of the planets are in the habitable zone. We believe that these 3, specifically E, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, and possibly also TRAPPIST-1d, are sort of the best candidates for, well, maybe somewhat Earth-like conditions. But for the longest time, we weren't really sure about what they're made out of. And so a study that was published a few months ago has actually established that TRAPPIST-1, B, C, D, E, and F were all most likely terrestrial planets. In other words, they were worlds that most likely contained rocky surfaces and resembled something like Mars or Venus or Mercury or possibly, if we're lucky, Earth. And many simulations that were done by various scientists presented these planets as either basically ice worlds or hot lava worlds, or at least very hot worlds, or possibly worlds filled with liquid water. But we weren't really sure about one of the more exciting planets, the most massive planet specifically, TRAPPIST-1g, which is this right here. This planet is very, very close to Earth in mass. It's only maybe 10% or 14% more massive, 1.14 masses of the Earth. And at the same time, its actual radius is also relatively similar to Earth, just a little bit, like 10% larger than Earth. And to us, that meant that this particular planet is very Earth-like in terms of both density and maybe even composition. The only problem was that we actually thought that maybe this is actually what's known as a super-Earth. In other words, maybe it's actually a gas-like planet. And for this reason, we actually had to try to find a way to study its atmosphere, or at least find a way to see what's happening here. And what this recent study discovered, a study by Hannah Wakeford from the Space Telescope Science Institute, was that, well, we now believe that the atmosphere of this planet doesn't contain any hydrogen and most likely changed over time. In other words, if the atmosphere changed, it's probably not a gas giant. It's probably not a gas dwarf or whatever you would call this. It's basically not a planet that has hydrogen atmosphere. It's most likely a planet that actually has its atmosphere changed over time, similar to how Earth's atmosphere changed as well. And for this study, they've actually used the Hubble telescope to try to see what we can actually detect here. And what they've discovered is that, well, it seems to indicate that the actual atmosphere of this planet evolved. And evolution of atmosphere is something that is sort of native to terrestrial planets. We know that Martian atmosphere evolved, we know that Venusian atmosphere evolved, and obviously Earth as well, because we didn't have any oxygen, for example, but now we do. And this of course suggested that TRAPPIST-1G most likely has both atmospheric and also geological activities on its surface. So once again, something that usually happens on a terrestrial world. I mean, we don't really know what happens inside Jupiter, like if it actually has a core and if it's a solid core. We don't really know if there's like Jupiter quakes. It's something that's possible, but there's no way for us to find out just now. But we do know that Mars has quakes, and so does Earth, and so does the Moon. So many of these objects will probably have geological activities, and it's very likely that TRAPPIST-1G is full of these activities. But however, there are obviously some challenges here. So one of the challenges, first of all, is that the current assumption is that due to the distance from the parent star, this planet is currently, the way it stands, is at minus 67 degrees Celsius. In Space Engine, it's actually even colder at minus 116 degrees Celsius. And that's because of the actual distances involved here. Now, if, however, this planet has very thick atmosphere, like for example, let's give it 1 atmosphere of pressure just to see how it changes, it might actually get more actual temperature needed to maybe even melt the liquid water here, in which case it might then be a liquid water like this one. However, all of this is still kind of speculatory, it's still an assumption. We don't really know what's happening here. But what we do know is that due to its size and mass and very, very similar sort of density to Earth, it's probably very Earth-like in terms of actual structure. It could be actually a water world like what you see here, but even if it's a water world, it still will have a relatively thick mantle and most likely a metallic core. And if it actually has metallic core, there's a chance for it to have magnetosphere, which might protect it from the biggest danger in the system, the very, very active star TRAPPIST-1. These stars, the red dwarfs, are actually really active. They have a lot of flares. They produce a tremendous amount of energy, as you can see just happening there right now. And for this reason, we believe that these stars are not super safe. They're probably some of the more unsafe stars, and they also tend to change a lot. They actually have a dramatic sudden increase in temperature and then they'll actually decrease again. But for TRAPPIST-1, it's surprisingly cold actually. The temperature of TRAPPIST-1 is only about 27 degrees Celsius, but what these scientists discovered is that it also has a tremendous amount of dark spots, dark patches, just like our sun. Here's actually a photo from NASA of several such spots. And normally these are formed by the actual magnetic lines of the star. And we believe that about 3% of the surface of TRAPPIST-1 is covered in these things. And these things are really hot. They're usually about 2,000 to 3,000 degrees hotter than the actual star. And so all of this suggests to us that TRAPPIST-1 is one crazy star. It's probably very active, it's probably very explosive, and once in a while raises the temperature of those planets by a few degrees, but only for maybe like a few minutes or so. So it does have a lot of flares, it has a lot of radiation that it produces. But at the same time, one of the recent studies by one of the professors from Harvard, Professor Loeb, discovered that it also seems that these particular stars, these red dwarfs, don't really produce enough visual light for things like plants or essentially photosynthesis to take effect. So if there is life, it's probably not photosynthetic life. And if we do come here one day to settle, we really are not going to benefit from bringing any plants because they're not going to get enough energy from the star to actually survive. Unless those plants are genetically modified to somehow use infrared or ultraviolet radiation. But on the other hand, the scientists who published this paper also kind of included a warning. And the warning here is that, well, you have to remember that these planets are relatively close to the parent star. The distance here is very, very low. Like if I were to compare this to where Earth is, so this is where Earth is, and this is where all of those other planets are, much, 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 much closer to the parent star. And because of this, they are actually kind of covered by the star's atmosphere. And some of these stars, including this one, actually do possess things like water vapor and obviously hydrogen and helium. And so we have to be aware of these false signals, basically, because if we suddenly detect water vapor, it doesn't mean that we're seeing this water vapor from a planetary atmosphere of beautiful TRAPPIST-1G. Maybe, just maybe, there is actually no water here at all. Maybe it's completely devoid of water, and maybe the water vapor is actually coming from the star. And so we have to be careful, but luckily the technique that these scientists developed is actually really good at basically distinguishing between water vapor from the star or water vapor from the atmosphere of a planet. But it's good that they mentioned this, because a lot of modern scientists sometimes forget to actually account for that. And so overall, it's actually a super interesting study, but I guess our next step is to find out what's happening with the last planet, TRAPPIST-1H. Is it just a cold, dead, icy world like we have right here? Or is there something really cool going on? But for what we know so far about TRAPPIST-1G, it suddenly has increased its chance of being possibly the most Earth-like planet we've discovered so far. Now, if we actually add a little bit of water here, and then scroll down to where this simulation calculates so-called Earth Similarity Index, you will discover that, surprisingly, the Earth similarity of this object is close to 96%. This is actually higher than any object in our solar system, including Mars. For comparison, Mars Earth Similarity Index, according to the simulation, is only about 65%, and it's something that might be very trivial, and it basically uses things like mass, density, and temperature to try to calculate this, but it does show you that, according to this new study, TRAPPIST-1G is probably one of the most unusual, but possibly also most Earth-like objects we've discovered to date. Very, very similar in density, very similar in even maybe temperature, depending on the atmospheric pressure here. But most importantly, it's in a system that has 6 other planets that might also give us a chance of finding that new Earth 2.0. However, one thing to remember is that it's super dark here. The sun, the star, TRAPPIST-1 doesn't produce enough visual radiation, and so standing on the surface of this planet, the actual daylight, or I guess midday, would look kind of something like this. It would be very, very, very dim, very dark. Only approximately 2% of the actual visual sunlight would reach the planet, and so it's kind of depressing. It's not very beautiful. But nevertheless, that's still one of those objects that I would honestly love to visit one day. Anyway, on that note, hopefully we'll discover more things about TRAPPIST-1 in the future, and if you still haven't subscribed, do subscribe, because we're going to come back and talk about this in one of the future videos. Thank you so much for watching, and thank you to all of you that support me on Patreon. It does help me tremendously, and I'm really thankful for all the support that's been given to me over the months and years. Anyway, thank you for watching, guys. I'll see you tomorrow. Come back tomorrow to learn something else. Space out, and as always, bye-bye.